Welkom allemaal. Welkom hier in de Stadsgehoorzaal in Leiden. Leiden is dit jaar in 2022 het middelpunt van de Europese wetenschap eigenlijk. Het is de European City of Science en talloze congressen en bijeenkomsten gaan we het eigenlijk hebben over wetenschap. Maar ook als belangrijk doel om hoe kunnen we nou eigenlijk wetenschap en de samenleving beter verbinden. En de samenleving is vandaag eigenlijk complexer dan ooit. De huidige generatie groeit op met coronapandemie, klimaatcrisis en zelfs nu ook oorlog binnen Europa. En hoewel de meeste kinderen zich over het algemeen best wel prima ontwikkelen, lukt dat niet iedereen om te slagen. En hoe kunnen we nou eigenlijk ervoor zorgen dat de ontwikkeling beter begeleiden? Dus eigenlijk hoe kunnen we zorgen voor optimale condities voor kinderen om op te groeien? Nou, daar wil ik het vandaag over hebben. En daarvoor heb ik twee hele bijzondere gasten. Károly Illy, kinderarts, voorzitter van de Nederlandse Vereniging Kindergeneeskunde en lid van het Outbreak Management Team. En Arne Popma, hoogleraar forensische psychiatrie, hoofdkinder- en jeugdpsychiatrie in het Amsterdam UMC en de voorzitter van de Nederlandse Vereniging voor Psychiatrie. Nou, ik ben ontzettend blij dat jullie hier zijn vandaag, dus alvast bedankt daarvoor. En jullie zijn beide erkende kinderartsen met vele jaren ervaring. En ja, ik vroeg me af, Arne, hoe is het nu anders om op te groeien dan bijvoorbeeld 10 of 20 jaar geleden? Wat is er veranderd in de samenleving?
Goh, wauw. Nou, veel. Ja, het is wel leuk dat je ons kinderartsen noemt trouwens. Hè? Want ik ben dus kinderpsychiater. Maar wij vinden eigenlijk ook wel dat we in elkaars verlengde zitten. Dus neem het maar even. Dus dank voor het compliment. Wat is veranderd? Ik heb zelf vaak een presentatie over dit onderwerp. En dan begin ik dat toen ik ging studeren in Amsterdam, dat was in 1993, toen was ik 18. En dan laat ik een foto van een telefooncel zien. Want ik woonde ergens op een zoldertje bij een Turkse familie, zonder badkamer. Dan ging ik bij vrienden ging ik douchen of bij de sportvereniging. En dan belde ik 1 keer per week met mijn ouders dat ik nog leefde. En dat was het, zou ik maar zeggen. Dus de hele sociale media of whatever was er niet. Je was niet bereikbaar. Het vergelijken tussen jongeren ging nog gewoon live op het schoolplein of in de kroeg, zou ik maar zeggen. Wat de jongeren in ieder geval nu mij in ieder geval ook heel veel vertellen, en wat natuurlijk ook wel veel uit onderzoek komt, is ook, ik kan me wel herinneren dat bijvoorbeeld middelbare school dat ik het wel spannend vond, examens of wat dan ook. Maar ik kan me niet herinneren dat ik me zo bewust was dat ik van alles moest halen en dat ik daar elke dag mee bezig was of zo. Dus de jongeren die een beetje hun eigen BV'tjes zijn geworden en een soort opgelegd krijgen van je moet aan jezelf werken. En die prestatiedruk die heel veel mensen ook terugrapporteren. Ik denk dat dat ook wel een groot verschil is. Dat zijn de eerste dingen die bij me opkomen.
En herken je dat, Károly? Dat juist omdat we meer mogelijkheden hebben, het misschien moeilijker is om nu op te groeien?
Ja, ik wil eigenlijk beginnen met een soort disclaimer eigenlijk. Want dit is wel heel erg buiten mijn comfortzone. Wat ik hier
voor mij
doe.
ook.
Want dit is... kijk, ik ben eigenlijk gewoon een kinderarts in Tiel of all places. Ik ben hier uitgenodigd om over wetenschap te praten. Ik doe niets aan wetenschap. Hier zitten allemaal hele slimme mensen en die allemaal wetenschappelijk... Ik doe er niets, dus dat is wel een belangrijke disclaimer wat mij betreft, bij deze. Ik herken het wel heel erg. Jij 93, ik 79 begonnen. Dus dat is, overigens wat dat betreft qua sociale media en mobiele telefoon natuurlijk exact dezelfde...
Precies, die telefooncel was er toen al.
Zo is het, dus precies hetzelfde. En ik herken heel erg wel het grote verschil nu met die prestatiedruk die er onder jullie ongetwijfeld is, maar die er ook al op de basisschool is, bij middelbare scholieren is, bij studenten is. Dat is echt denk ik een heel groot verschil met, 10, 20 jaar geleden. Ik denk dat daar lijden uiteindelijk ook kinderen en jongvolwassenen onder. Ik denk dat het goed is om daar meer aandacht aan te schenken.
Ja. Nou, je zei al, ik ben geen wetenschapper, dus het is uit of mijn comfortzone. Maar jullie stonden natuurlijk wel allebei echt in de frontlinie van de pandemie. De gesprekken over de coronamaatregelen. Ja, wat is daarin jullie persoonlijke ervaringen? Hoe hebben jullie de afgelopen 2 jaar echt beleefd?
Nou ja, kijk, om even toch het bruggetje dan te maken naar de wetenschap. Ik ga je een voorbeeld geven. Vorig jaar, in de loop der tijd, en dat kwam ook door de contacten met Arne, begon ik me steeds meer, naarmate de pandemie vorderde, steeds meer te realiseren. Had ik natuurlijk eerder moeten realiseren, maar nou ja, ik ben ook maar een mens, dus ik heb me dat later gerealiseerd, hoeveel impact alle maatregelen hadden, ook op de jongvolwassenen. En zeg maar de groep van 15 tot 25. En dat was een groep die mijns inziens eigenlijk onderbelicht werd, terwijl dat de groep is die misschien wel het meest geraakt werd door alle maatregelen die we met z'n allen genomen hebben. En nou goed, op een gegeven moment kon er weer iets meer, maar de vraag was hoe dan? En toen heb ik dus gebruik gemaakt van studenten in het land om mij te helpen om de juiste documenten te geven hoe het OMT te overreden om de kennismakingstijd weer in 2021 te laten beginnen, om de introductieweken weer te laten beginnen en om op 1 september weer fysiek te kunnen gaan studeren. En ik heb dus eigenlijk niets aan gedaan. Ik heb alleen maar input gegeven aan hele slimme studenten uit Delft en Leiden en Groningen. En die zijn aan de slag gegaan, die hebben een prachtig document gegeven. En dat document heb ik vervolgens kunnen verdedigen in het OMT. En vervolgens is dat ook gelukt. Dus ja, ik heb wel gebruik gemaakt van de wetenschap, juist om meer mogelijk te maken voor kinderen en jongvolwassenen.
Ja, heel mooi. Hè? Ja.
Ja, nou, voor mij was het, we hadden het net over, ik vroeg net aan Károly vooraf, ga je een boek schrijven of zo? En toen zei hij van, nou, dat is een brug te ver. Maar voor mij is het ook dat was echt een hele ingewikkelde en interessante tijd. Het was, kijk, ik hoop dat als we naar de toekomst kijken en nu gaan nadenken, wat als nog een keer iets gebeurt zoals dit of iets anders. Je zou kunnen zeggen, misschien moeten we zorgen dat er wat meer psychologen en psychiaters en et cetera een sterkere stem hebben om dit vast te houden, waar nu de urgentie zo goed op zit. Tegelijkertijd was het heel fijn dat Károly er zat. En nou, we hebben heel veel respect voor hoe open jij bleef staan voor al die input. Want er komen nogal wat mensen op je af met hun belangetjes, zou ik maar zeggen. Maar het was heel fijn dat dus die mentale gezondheid en die jeugd bij jou in goede handen was. En dan zaten we ook wel eens in overlegjes tussendoor. Van wat zijn nou de goede argumenten, wie moeten we bij elkaar brengen. En ik zat er zeg maar in een soort ondergrondsgroepje, zal ik maar zeggen. Met allemaal de mensen van de jeugdbescherming, van de jeugdzorg. En breed voor de jeugd, zeg maar bij VWS, dan merk je ook hoe zo'n departement dan weer probeert voor de jongeren op te komen. Maar ja, dan ook zegt, nou ja, als jij dan nog Károly even belt, dan doen wij het nog zo. En dan probeer je het een beetje over de bühne te krijgen met z'n allen. En wat ik het heel mooie vind aan de coronatijd, is dat, kijk, ik vind zelf dat wij zijn zo versnipperd als wetenschappers, als zorg, als mensen die om jongeren heen kunnen gaan staan. We hebben dat eigenlijk zo matig georganiseerd in zo'n rijk land als we zijn. En wat ik echt als gewoon super gaaf heb ervaren, is dat we hebben in het begin zaten wij ook dagelijks met dat groepje bij elkaar. En dan moest er bijvoorbeeld een richtlijn komen van hoe ga je het gesprek aan met kinderen of beschermingsmaatregelen in de jeugdzorg. En dat was dus niet meteen geregeld. En dan hadden we gewoon binnen een dag zeg maar alle beroepsverenigingen, ook de kinderartsen, de staatssecretaris erbij. Iedereen gewoon binnen een dag, zo moet het doen, knallen met die handel. En ja, ik hoop een beetje dat we zeg maar, toch een soort relaties voor het leven hebben opgebouwd. Ook in de wetenschap. Er zijn ook met Eveline hele mooie, van die soort convergerend leiderschap, weet je wel. Laat die ego's even opzij. Waar gaat het nou echt om? In een crisistijd is dat heel lekker dat daar weinig discussie over is. Ik bedoel, bij jullie was het echt ingewikkeld, want jullie zaten echt rechtstreeks de politiek natuurlijk te adviseren. Maar bij ons konden we eigenlijk elkaar heel goed opzoeken. Dus ik hoop heel erg dat we ook naar een soort building back better, dat we daar aan toe komen. Ik maak me wel een beetje zorgen hoe snel de aandacht alweer een beetje verslapt van het onderwerp. En nou, met de akelige oorlog in de Oekraïne die ook weer een tik uitdeelt voor sommige jongeren. Nou, daar ben ik wel benieuwd naar of we dat momentum vasthouden.
Ja. Dus eigenlijk zeg je enerzijds, zo'n crisis maakt ons eigenlijk best wel efficiënt. Of in ieder geval hebben we allemaal hetzelfde doel voor ogen en zorgt dat we beter met elkaar praten. Tegelijkertijd is nu de samenleving heeft heel veel crisis.
Ja.
Wat ik net al noemde, verschillende dingen waar jongeren nu in opgroeien. Hoe kunnen we er dan voor zorgen dat we wel bij elkaar blijven praten? En wat zorgt er dan voor dat we die optimale condities om op te groeien kunnen waarborgen? We weten nu dat een coronapandemie niet optimaal is om in op te groeien. Maar wat dan wel?
Nou, we kunnen een paar dingen langs gaan denken. Volgens mij is één ding wat Károly net ook al aanhaalde, is dat de stem van de jongeren echt borgen en hun ook helpen zich te organiseren, wat jullie ook doen. En die politiek gewicht geven, dat is denk ik één ding. Snap je? We hebben veel te lang voor jongeren gedacht. En we weten allemaal intussen dat ik hoop dat dat wel echt zichtbaar is geworden. Wat voor slimme ideeën die gewoon zelf hebben. Dus, en daar zijn ook natuurlijk nu met citizen science en er zijn allerlei mooie nieuwe manieren om gewoon dat hele reservoir aan diversiteit ook, want niet elke jongere heeft hetzelfde nodig, aan te boren en die mee te laten denken. Dat is denk ik in ieder geval één heel belangrijk ding. En bijvoorbeeld een haakje is denk ik dat er is een preventieakkoord, dat weten jullie misschien allemaal. En daarin staat nu eindelijk door Paul Blokhuis nog, maar daar ben ik nog steeds fan van. Die heeft dus de mentale gezondheid in dat preventieakkoord nu geschreven. En dan kan deze secretaris nu gaan oppakken. We gaan volgende week een hele spannende meeting hebben, omdat daar heeft Károly ook al een keer een beetje over meegedacht, dat de koningin ook van plan is om op dit onderwerp zich te gaan verbinden aan een heel lang programma. Dus er zijn wel een paar van die soort dingen waardoor ik denk, oké, het momentum houden we vast. Maar ik ga denk ik een heleboel samenhorigheid houden. En volgens mij moeten wij dat met elkaar gaan voor elkaar krijgen, snap je? Dus zodra wij weer op onze eigen eilandjes terugtrekken en voor onze publicaties alleen maar gaan. Dus volgens mij hebben we het ook een beetje zelf in de hand. Als wij gewoon zorgen dat we klaarstaan en met een goed plan
maar wel
losgaan.
met input van de jongeren.
Absoluut.
Want ik denk dat in ieder geval pre-corona, denk ik dat er echt wel aan ontbroken heeft. En dat is, ik ben er best wel van overtuigd dat we dat niet meer gaan verliezen eigenlijk. Volgens mij is dat kwartje overal gevallen. Het OMT bestaat niet meer, maar of bestaat, is slapend zeg maar. Maar de wijze waarop besluitvorming heeft plaatsgevonden, het was wel iedereen duidelijk dat de argumenten waren aangedragen door jongeren. En dat ik was dan de spreekbuis, omdat er geen jongeren in dat OMT zitten. Maar ik kon wel aangeven dat dat de input was gegeven door jongeren. En ik denk echt wel dat we dat niet meer gaan verliezen. Ik ben er erg van overtuigd dat wel blijvend is. Ja,
ik hoop het ook ontzettend, maar ik denk ook wel dat het zich heeft bewezen, dat er meer draagkracht voor is. En Károly, je zei net al, ik heb nu door de pandemie en door mijn plek in het OMT ook wat meer de wetenschap opgezocht en dat daar mijn info vandaan gehaald of dat meer in verdiept. En denk je dat dat blijft? Hoop je dat? Want dat is natuurlijk ook die belangrijke schakel tussen wetenschap en samenleving is dan heel breed. Maar ik bedoel zelfs tussen wetenschap en uiteindelijk kinderartsen, die liggen nog een stuk dichter bij elkaar. En
ja, maar kijk, het is niet zo dat de wetenschap een probleem is onder kinderartsen. Dus er zijn voldoende kinderartsen die...
Nee, maar ik bedoel vice versa, hè? Want andersom is het voor een wetenschapper soms ook wel heel nuttig om zich te laten informeren door bijvoorbeeld een kinderarts.
Nee, zeker. Maar ik bedoel alleen maar zeggen, er zijn ook een heleboel kinderartsen die uitermate wetenschappelijk bezig zijn en die dus heel erg daar heel veel tijd en energie en aandacht aan schenken. Weet je, het is absoluut zo dat ook bij mij... ook gewoon in mijn dagelijks werk heb ik er ook dus ik heb een soort van wedervraag aan Arne. We hebben het best wel, als ik er eventjes mag wat.
Zeker.
We hebben de afgelopen periode best wel vaak stilgestaan bij de restschade of de langetermijnschade die zou kunnen ontstaan. Tegelijkertijd merk ik in mijn spreekkamer, en ik heb toevallig een bijzondere patiëntenpopulatie omdat ik ADHD als specialiteit heb. Dus ik zie heel veel tieners en ook enkele jongvolwassenen. Ik merk wel heel veel veerkracht.
Zeker.
Dus we hebben veel gehad over schade. Maar ik merk ook wel, gewoon in de dagelijkse praktijk, we hebben ons er zorgen over gemaakt, maar top zoals jij er nu uitkomt en zoals jij nu weer gewoon volop in het leven staat. Dus valt daar iets van te zeggen al, is het nog te vroeg daarvoor?
Valt het eigenlijk wel mee, Arne?
Ja, kijk, dit vond ik zelf, even één stap terug, tijdens de pandemie eigenlijk het moeilijkste onderwerp. Want wat wij op goed moment zijn gaan gebruiken is het stoplichtmodel. Om het een beetje überhaupt over de bühne. Kijk, het eerlijke verhaal is natuurlijk, dat weten wij allemaal, dat jongeren zo verschillend zijn als je maar kan verzinnen. En bijvoorbeeld wij hebben heel langlopend nu al intussen onderzoek gedaan. En dan bij ons was ongeveer 5% van de normale populatie die zei, top, heerlijk, die pandemie, lekker rustig. Was er ongeveer 60-70%, vervelend, maar En dan had je dus, daarna kwam het groepje wat wij dan subklinische problemen noemen, het oranje en het rode. En die groep die was tijdens de eerste lockdown in onze meting in ieder geval verdubbeld. Dubbel zo groot qua het aantal kinderen die echt in het rood schoten, qua mentale problemen, internaliserende problemen. Tinker Polderman zit hier ook ergens die dat onderzoek leidt. En aan de laatste meting is het nog steeds keer 1,5 dat groepje. Kijk, en op gemiddeld, op heel Nederland, kan je zeggen, het gaat eigenlijk met heel veel heel goed. En dat is steeds het genuanceerde verhaal. Maar af en toe hebben wij de focus echt even gelegd op die rode groep. Omdat die dreigt eraan om nog door te gaan. En je moet je voorstellen dat we ook in de GGZ, en zeker bijvoorbeeld rondom eetstoornissen, dwangstoornissen. Dat liep, onze IC's hebben een tijdje lang ook echt gepiept en gekraakt. En ons personeel nog steeds, moet ik zeggen. Dus de druk op de zorg. Dus nog een keer gemiddeld heel veel veerkracht. Super interessant om nu te kijken wie van die oranje-rode groep weer terugschiet naar groen. Ik ben er ook best wel optimistisch over. Maar een verdubbeling van kinderen met op psychiatrisch niveau klachten. Dat is ook wel goed om te realiseren. Er zijn cohorten in Nederland die al 40 jaar onderzoek doen. Die hebben nog nooit één gerimpeling in dit soort getallen. Nooit. Nee. En nu wel. Ja. Dus zelfs dat kleine groepje op het geheel is toch een verdubbeling, vind ik heel veel. Dus die diversiteit zit erin.
Dat herken ik overigens ook hoor, want die groep helemaal aan de bovenkant van de piramide, zeg maar. Alle Nederlandse kinderartsen zien een enorme toename van het aantal kinderen met eetstoornissen. Er moet geleurd worden, tussen aanhalingstekens, met kinderen die ergens op een spoedeisende hulp zitten en waarvoor geen plek is in ziekenhuis A. En dan zit ik in een appgroep met van ieder ziekenhuis een kinderarts. Heb jij plek? Wie heeft er plek voor dit meisje in Amsterdam? Nou, die gaat dan naar Winterswijk of naar Tiel of naar Sneek. Of, dat gaat heel Nederland door. Omdat het zo toeneemt en omdat het en dat is dan eventjes een intern probleem, maar je kunt als kinderafdeling niet te veel van dit soort patiënten hebben, omdat het voor verpleging is het de meest intensieve, maar ook mentaal intensieve groep. Dus dat heeft zo zijn grenzen. Ja.
Misschien nog iets over die diversiteit. Dat is natuurlijk ook nu zo interessant. Ik las net nog ergens een NOS-app van een meisje met astma die heel vaak niet naar school kon vroeger en die dan in de pandemie lekker thuis alle lessen konden volgen en die nu niet meer die online les kan volgen van school. En dat vind ik ook zo'n voorbeeld. Wat hebben we nou geleerd aan wat zou je op maat meer voor jongeren kunnen inregelen? Hè? En dan hoop ik dat we die flexibiliteit ook, dus dat je juist geleerd van wat er eigenlijk zo prettig was in die tijd, wat er modern op te lossen is. En ik hoop wel dat we niet weer helemaal terugveren daarin. Ja. En ook daar die jongeren wel aan het roer laten.
Ook optimale condities op individueel niveau.
Ja.
En jullie hadden het net al even over dat het eigenlijk het grootste deel eigenlijk best wel relatief veerkrachtig is. En dat zei ik ook al, die komen best wel oké terecht, gaan zonder al te veel kleerscheuren door die adolescentie. Maar er is ook een groep die heeft het wel heel moeilijk. Die groep is gelukkig beduidend kleiner. Maar als we nu willen nadenken over optimale condities om op te groeien, op welke groep moet je je dan focussen? Pak je die hele grote groep die het goed doet, dus die kan laten zien wat zijn optimale condities zijn? Of pak je die kleinere groep die misschien meer hulp nodig heeft om ook die optimale condities? Ja.
Waarom?
Moet.
Nee, maar waar leg je je prioriteit?
Waar leg je je prioriteit?
Nou, ik denk dat je toch in alle gevallen je prioriteit moet leggen bij de allerkwetsbaarsten, eerlijk gezegd. En dat is dan toch de groep die het meest zwaar heeft en het meest te lijden heeft gehad en nog steeds lijdt. Dus ik ben er wel van overtuigd dat daar zullen we serieus en het meest serieus aandacht voor moeten hebben. Maar ja, het is wat Arne zegt, moeten we kiezen. Als je moet kiezen, dan zou ik zeggen, daar in ieder geval voor. Maar het is natuurlijk superbelangrijk dat we die grote andere groep niet in de steek laten. En dat we daar ook wel aandacht voor blijven houden.
Ja, kijk, ik ben er steeds meer van overtuigd eigenlijk dat we dus... we hebben in Nederland de publieke gezondheidszorg, maar we hebben eigenlijk nauwelijks een publieke mentale gezondheidszorg. En terwijl er zijn hele mooie, gewoon simpele overzichten. Je kan een universele preventie doen, meer getargete preventie. En zo kan je het heel mooi opbouwen. En ja, ik vind het eigenlijk frustrerend dat we het in Nederland nog niet zo georganiseerd hebben. Gewoon puur vanuit kennis, dat je op alle niveaus het doet wat bewezen effectief is. Hè? Dus bijvoorbeeld. Want mijn punt is, je hoeft helemaal niet meer geld erin te pompen. Je moet het geld gewoon anders verdelen. Dus bijvoorbeeld die 8 miljard die dan nu naar het onderwijs gegaan is. Elke school een ton succes ermee. Ja, dat vind ik echt schandalig. Terwijl er is bijvoorbeeld er zijn bewezen effectieve antipestprogramma's of brede schoolaanpak waarbij IQ verhoogt, waarbij sociaal-emotioneel leren gestimuleerd wordt. Allerlei positieve effecten op de lange termijn. Er zijn in Nederland ongeveer 10% van de scholen heeft zoiets geïmplementeerd. Ja, ik vind dat echt onzin. Ik snap dat niet. Het goede ervan, nieuws, is dat bijvoorbeeld toch ook weer door die corona-epidemie er wel iets aan het schuiven is in het onderwijs, dat ze het belangrijker gaan vinden en dat ze het aan het oppakken zijn. Maar het is een voorbeeld waarin je, als je het in het schoolprogramma opneemt, hoeft er helemaal geen geld bij, maar je bent wel aan preventie aan het doen. En wat er ook mooi aan is, en dat hoop ik ook dat we dat steeds voor elkaar houden, is dat je het niet zo individualiseert. Hè? Dus bepaalde kwetsbare kinderen. Als we daar alleen maar individueel op gaan interveneren, dan zeggen wij dus eigenlijk zelf, jij bent het probleem. Terwijl we weten dat grote klassen is gewoon een probleem. Je zou die klas gewoon naar 20 terug kunnen brengen. Bijvoorbeeld, of je zou kunnen zeggen met zo'n brede schoolaanpak, wij hebben een manier om met diversiteit in onze klas om te gaan. Er zijn hele mooie, bewezen effectieve programma's om leraren, docenten te trainen in omgaan met agressief gedrag van kinderen. Waarin je dus de hulpverlener meer die docent steunt en zo normaal mogelijk dus dat gedrag een beetje laat mediëren. Ja, ik denk dus dat we niet hoeven kiezen. Maar ik denk dat we wel, waar we moeten kiezen, is niet 20 schoolbrede programma's, maar 1 of 3 of zo. En dan 1 van die 3 kiezen en succes. En dan gaan we ook nog een beetje leren en ontwikkelen. En zo zouden we, daar wil ik graag mijn energie voor inzetten. Snap je? Dat we een beetje de rommel opruimen en gewoon wat bewezen effectieve dingen met elkaar gaan doen.
Dus niet kiezen tussen de veerkrachtige of de kwetsbare, maar naar het geheel kijken eigenlijk. En daarbij ze automatisch wat meer bij elkaar toetrekken, of dat de kwetsbare wat...
Nou, dat is ook goed aan hoe wij hier zitten. Dat wij zitten zeg maar aan de achterkant bij de kinderen die echt in problemen zijn gekomen. Dat we met elkaar aan het praten zijn. En we hebben ook een paar hele mooie projecten nu waarin we zeggen, we moeten in het ziekenhuis bij wijze van spreken op dezelfde manier mentale gezondheid gaan meten als in de bevolking. Dat doen we op dit moment helemaal niet en dat vergelijken we niet met elkaar. Zodat we kunnen gaan kijken, kunnen we dingen verzinnen zodat minder kinderen aan die achterkant belanden. Nou, zo'n infrastructuur bouwen, alleen dat als we dat voor elkaar kunnen krijgen, dan hebben we ook naar de politiek toe wat cijfers waarmee we kunnen zeggen, als je nou hierop investeert, dan krijg je het daar terug. moeilijk is daarbij, het duurt wel 10 jaar of 20 jaar. Dus we hebben wel, daar is bijvoorbeeld de koningin volgens mij heel goed voor. Want dat vertelde haar persoonlijke assistent. Die zei, weet je Arne, de koningin die is geduldig. Die zit er over 10 jaar nog. Weet je wel? Dus van dat soort types moeten we volgens mij een beetje gebruik maken. En wij zitten er over 40 jaar ook nog, als we ons werk een beetje leuk vinden. Dus de continuïteit moet van ons komen.
Ja, aan de andere kant, wat volgens mij is, maar er zijn anderen die dat vast beter weten in deze zaal wellicht, maar is het zo dat gemiddeld genomen er eigenlijk niet echt een grote onderwijsachterstand is opgelopen in coronatijd, maar de verschillen tussen kansarme en de kansrijke kinderen zijn wel toegenomen. Dus gemiddeld is het ongeveer hetzelfde, maar de kansarme kinderen uit de Schilderswijk en elders, die hebben het veel moeilijk, of kinderen met een niet-westerse migratieachtergrond. Ja. Dat fenomeen, ik weet het niet, maar ik gok dat fenomeen enerzijds leidt natuurlijk tot onderwijsachterstand, maar het is niet ondenkbaar dat ook leidt tot mentale problemen. Dus het is een combinatie van dingen die groep kinderen...
Ja, het helemaal gelijk.
Daarom gaf ik antwoord zoals ik er antwoord op gaf. Ik vind het wel heel belangrijk dat we daar wel serieus aandacht aan moeten schenken.
Nee, zeker. Alleen, mijn punt is eigenlijk meer, laten we niet doorschieten in die kinderen problematiseren en weer apart zetten en met nog een overdonderen met allerlei extra werk, zou ik maar zeggen. En ook in de taal oppassen dat we niet hun als het probleem, maar de abnormale situatie als het probleem blijven benoemen. En dat je ook als klas daar iets mee kan. Hè? Dat je niet dat je als groep daar iets mee kan. Ik denk zelf dat wij als dokters gewend zijn om zeg maar dat ene kind voor je neus te hebben en dan te zeggen, hè, wat is het probleem, dat gaan we fixen. Dat is soms super nodig en dat ook goed. Maar in die publieke gezondheidszorg, of hoe je het ook wil noemen, dat publieke domein, dat we daar moeten oppassen dat we die kinderen stiekem eigenlijk dus weer zeggen, nou, je faalt als jij niet meekomt. Hè? Want we moeten kijken wat we je allemaal aanbieden. Nou ja, daar zit ik veel over na te denken.
Ja. Nou, je had het net natuurlijk ook al over die preventieprogramma's. Als je echt kijkt naar de focus op de kwetsbaren, dan zou je het misschien kunnen zien als bijna een beetje symptoombestrijding. Van hoe krijgen we dit nog een beetje op het goede pad? Terwijl je als je meer op die preventie kan zitten en kunt kijken wat maakt nou die factoren dat het ene kind in een moeilijke situatie wel kan floreren en de andere niet. Ja, dat zijn natuurlijk die optimale condities die we zo graag zouden willen weten. En ik vroeg me af, Károly, in je gesprekken met studenten en de jongeren in het schoolpleidooi, is dat ook iets wat je van hun meekreeg? Dat school ook belangrijk is voor hun mentale gezondheid, maar misschien ook wel fysieke gezondheid? Of, waarom wilden ze eigenlijk zo graag naar school?
Ja, wat eigenlijk heel breed door iedereen werd gezegd, dat zijn de sociale contacten. Dus het is niet zo per se dat ze in die collegezaal willen zitten. En ook niet per se dat ze op de middelbare school naar school wilden gaan. Maar het was en is het belangrijkste, is en was de belangrijkste plek waar ze peers ontmoeten. Dus het gaat natuurlijk, is het ook belangrijk dat je dat onderwijs, maar dat was hun punt niet. Hun punt is, we willen mensen ontmoeten. En zolang de horeca dicht is, ontmoeten we daar geen mensen. En dus willen we naar school, zodat we weer gewoon onze klasgenootjes, onze collega-studenten weer kunnen ontmoeten. Dat is hun allerbelangrijkste. En daar zijn ook de studies die ik vervolgens via Arne krijg en via die studenten krijg en die vervolgens ook gedeeld zijn met het OMT. Daar is dat eigenlijk allemaal. En dat zijn eerlijk gezegd prachtige internationale studies die ook aantonen hoe ontzettend belangrijk de sociale contacten zijn voor het mentale welbevinden.
Periode, in die, eigenlijk wat je kwalitatieve jaren zijn, zeg maar, in de ontwikkeling.
Precies.
Nou, jullie hebben allebei ook heel erg gepleit voor die rechten van adolescenten, voor meer aandacht ervoor. Geef ze letterlijk meer beweegruimte, want ze moeten zich nu ontwikkelen. En er zijn ook wel wat kritische debatten geweest, want we hebben natuurlijk veel gezorgd voor de kwetsbare ouderen, ze veiliggesteld en daardoor de jongeren misschien wat beperkt in hun ontwikkeling. Zou je niet veel beter moeten investeren in die kwalitatief goede jaren ten opzichte van mensen maar zo lang mogelijk in leven houden?
Ja, weet je, dit vind ik een duivels dilemma. En dat is een duivels dilemma in dat OMT ook voortdurend geweest, waarbij er ook hele pittige discussies zijn geweest. Omdat natuurlijk, of niet natuurlijk, maar het OMT heeft langdurig als enige en belangrijkste parameter gebruikt het aantal ziekenhuisopnames, maar vooral het aantal IC-opnames. Er moesten gewoon zo weinig mogelijk mensen, lees bejaarden, doodgaan. En dan ook nog bejaarden die iets onder de leden hebben. Die dus sowieso al eerder doodgaan omdat ze iets onder de leden hebben. Ja, dat is kwantificeerbaar. Dat is min of meer meetbaar. En daar zijn de modellen van het LIVM. Iedere week zien wij dan die modellen aan ons voorbij trekken. En zien we wat als deze maatregel wordt doorgevoerd, wat betekent dat dan voor het aantal IC-opnames over 1, 2, 3, 4 weken? En wat betekent dat dan voor het aantal doden? Dus dat kun je precies allemaal berekenen en vaststellen. Wat niet kwantificeerbaar is, maar ja, waar ik, maar ook Diederik Gommers en een paar anderen in het OMT ons wel hard voor gemaakt hebben, maar wat veel lastiger is, dat is die mentale schade. Onder jongeren. Want dan wordt er gezegd, ja, maar er is ook veerkracht, waar we het net over hadden. Maar hoe weeg je dat? Hoe weeg je dat op die weegschaal? En durf het maar eens. Durf maar eens te zeggen, ga maar eens in zo'n OMT zitten en zeggen, ja, het is wel lullig voor die bejaarden, maar we gaan nu echt de scholen open doen. En dan moeten we maar, dan stromen de IC's maar vol en dan moeten we maar aan de poort triëren. Jij gaat wel naar de IC en jij niet en dus ga je dood. Nou, dat is niet makkelijk. Nee. En dus het is een duivels dilemma waar iedere week, of in ieder geval heel erg veel over gediscussieerd is. En waar ik ook slapeloze nachten van gehad heb. Absoluut. Heel lastig.
Arne?
Nee, ik vind dat mooi om te horen en dat heb ik ook wel ervaren. Wat bij mij nu in ieder geval opkomt, ik denk dat we deze discussie sowieso aan moeten, even los van corona. Ja, we worden. Dus Johan Makkelbach heet hij, als het goed is, de oud-hoogleraar publieke gezondheid, die had een hele mooie afscheidsreden die ging over in ons streven naar een betere wereld creëren we onze eigen ziektes. Dus we worden allemaal, weet ik veel hoeveel ouder dan 100 jaar geleden. Dus even los van corona, we moeten nadenken over hoe we onze maatschappij draaiende willen houden en hoeveel kosten we in de laatste levensjaren willen besteden. En ik denk, wel, ja, ook los dus van corona, dat we veel meer aan de voorkant moeten investeren. Er zijn nogmaals heel veel effectieve, goede dingen die je kan doen. We hebben al die kinderen, jongeren, eerlijk gezegd ook gewoon nodig om de maatschappij draaiende te houden.
Want dat is nog een crisis die er bovenop komt. De generatie die steeds ouder wordt, de vergrijzing, de populatie, de verstedelijking daarin. Dat komt eigenlijk allemaal op die schouders van die jongeren die nu dus best wel een knauw hebben gehad.
Ja, en het is ook denk ik terecht dat zij zeggen, wij gaan opdraaien voor een heleboel dingen die we nu even overeind hebben gehouden. Laten we ervan uitgaan dat het gewoon nodig was. Dat denk ik ook wel echt. Maar dan hebben we nu iets te compenseren en we hebben iets slim te doen met die discussie. En in de kliniek, ik werk veel met de jongeren die ook nog wel eens een beetje boos worden, zou ik maar zeggen. En dan hebben we dus het adagium, smeet het ijzer als het koud is. Dus je gaat niet midden in als het helemaal escaleert, ga je dingen proberen op te lossen of tijdens een crisis. Maar juist als het rustig is. Dus eigenlijk nu is het moment waarin we dit morele dilemma, wat het gewoon is, moeten uitwerken. En bij mij weten lager erop.
Misschien moet het OMT toch nog even wakker worden en nu doorpakken.
Nou ja, weet je, ik ga ervan uit dat dit gaat natuurlijk uitgebreid geëvalueerd worden. En we gaan ook nog wel bij elkaar komen voor de evaluatie. Jongens, en dat zal niet een middagje zijn. Pardon. Daar zullen we echt veel tijd voor gaan nemen, als OMT ook, om samen te beoordelen wat hebben we goed gedaan. Er zijn toch ook hopelijk dingen die we goed gedaan hebben.
Absoluut.
Maar vooral, wat kunnen we hiervan leren? Want al was het maar, omdat, niemand die het weet, maar er kan natuurlijk in november weer een variant komen waar we heel veel last van kunnen gaan krijgen. En dus we hebben de plicht om goed te evalueren hoe hebben wij dit aangepakt. En dan gaan dit soort aspecten, die gaan we daarin meenemen, absoluut.
En dan wordt het anders?
Wellicht, maar dat weet ik niet.
Nou, bijvoorbeeld wat misschien nog wel leuk is om te vertellen, is dat er ook een hele groep bezig is om die modellen die dan, waar je het over hebt, er zijn allerlei ook wel best wel knappe modelleurs nu bezig, bijvoorbeeld met modellen maken voor suïcide of voor eenzaamheid. En dat vind ik een heel interessant, hè, want het is lastiger kwantificeerbaar. Maar het is best kwantificeerbaar, snap je? Wij doen niet anders in de psychiatrie dan dat we dingen die je niet kan zien toch proberen te kwantificeren. Nou, dat is best lastig, maar we hebben er wel ideeën over. En
klopt het ook af en toe.
En dan klopt het ook nog af en toe. Zelfs vaker dan de foutmarge bij jullie modellen. Nee, maar ik maak er een grapje van. Maar ik denk dat dat ook iets is wat wij, zal ik dan maar even zeggen, kunnen oppakken. Als wij nou denken over mentale gezondheid, of hoe je het ook, of weerbaarheid, maakt me allemaal niet uit. Hoe kunnen wij het dan kwantificeren? Want het ligt ook aan ons. Ik kon Károly ook dus niet dat model geven van wil je dit plaatje laten zien bij de vergadering.
Dus eigenlijk moeten we er naar een manier toe waarop we hopelijk in een fictieve nieuwe pandemie en de sterftecijfers hebben en de impact op het mentale.
Ja. Nou kijk, één ding is wat mij betreft echt zeker. Het is een vergissing geweest. En dat heb ik ook in het OMT, heb ik ook wel eens tegen Jaap van Dissel gezegd. Het is echt een vergissing geweest dat de mentale gezondheid geen plek had in het OMT. Er zijn allemaal mensen die vonden dat de economie erin moest, sociologie, dat ben ik niet mee eens. Maar het is een medisch-wetenschappelijk OMT. En medisch-wetenschappelijk, daar is geen twijfel over mogelijk. Daar hoort dus ook de psychiatrie bij. Dat is denk ik echt een vergissing. Er zaten 12 microbiologen in. En geen psychiater. Dat is belachelijk. Ja. He, dus of belachelijk, nou ja, goed.
Dat mag, in deze ruimte.
Het wordt gefilmd.
Ja.
Nou, dat is denk ik een vergissing geweest.
Ja, dus dat is, als we het moeten hebben over een soort call for action,
zeker,
dan is dat...
Zeker, absoluut.
Er moeten meer...
Vind ik erg.
We moeten het niet meer zien als fysieke versus mentale gezondheid,
nee,
maar
het is een
gezondheid.
Onderdeel van de gezondheid, precies.
Ja, dus oproep aan de zaal.
En in zekere zin is het ook wetenschap.
Zekere zin. In zekere zin is het kwantificeerbaar.
Ongeveer, om en nabij. En Arne, je gaf net al aan, ik hoop dat we goed met elkaar blijven praten en zo doelgericht blijven en niet weer terug naar onze eilandjes om te publiceren. Ja. Er zitten hier ook heel veel jonge wetenschappers in de zaal. Die willen misschien wel heel graag in de wetenschap blijven. Maar die moeten daarvoor wel op hun eilandje publiceren. Hoe gaan we dat dan oplossen?
Ja, hoe gaan we dat oplossen? Nou kijk, ik denk dat het... ook daar kan je weer aan heel veel knoppen draaien. Dus mooie publicaties, voor alle helderheid, superbelangrijk. Het is gewoon een goed onderdeel van ons vak. En dat moeten we ook zeker blijven doen. Daar kunnen we ook trots op zijn. Maar een beetje de balans zoeken in dat stukje en andere parameters van impact hebben. Zoals iets voor elkaar krijgen in beleid of iets toepasbaar maken op een school of weet ik veel wat. Ja, ik als afdelingshoofd, en volgens mij is Eveline daar ook een goed voorbeeld van. Je kunt natuurlijk wel degelijk met je eigen groep een beetje daarop letten. Met elkaar afspreken van waar gaan wij voor? Wat is uiteindelijk wat we willen bereiken? Je kunt inregelen dat je dus jongeren betrekt bij je onderzoeksvragen. En zitten we iets te doen waar jongeren ook op zitten te wachten. En we hadden even een voorgesprek. Toen zei je ook van ja, maar je moet toch ook wel een beetje gewoon... Hè, Blue Sky noemde je het geloof ik. Hè, een beetje zo van gewoon de nieuwsgierige wetenschap moet ook een plek hebben. Dat vind ik ook. Daar moet ook ruimte voor zijn. Alleen, ik denk dat wij als wetenschappers zelf een manier moeten verzinnen om daar een beetje in teamverband elkaar de ruimte voor te gunnen. En dat je dan als team hebt, weet ik veel, als je een voetbalteam hebt en je hebt 11 Messi's, ja, dan verlies je de wedstrijd. Maar eentje is wel heel lekker om in je team te hebben. En die moet ook eigenlijk gewoon lekker doen wat die maakt niet uit. Succes, weet je wel. Maar je hebt ook een Virgil van Dijk achterin nodig en een keeper. En, kijk,
die heeft ze allemaal van voetbal.
Volgt iedereen het nog of is iedereen afgaat? En die teamsport mag je ook invullen.
Een aanvaller en een verdediger.
Ja, precies. Dankjewel, dat is een goeie. Ik denk altijd voetbal. Maar nou, kijk, dus daar kan je... wat mijn punt is, dat moeten we zelf verzinnen en zelf zorgen dat niet allerlei instanties als NWO of de politiek ons gaan opleggen wat onze doelen zouden moeten zijn. Snap je? Die vrijheid moeten wij zelf creëren en dat moeten we toch wel doen door elkaar een beetje iets te gunnen en van elkaar te weten wat we aan het doen zijn. Bijvoorbeeld bij ons op de afdeling heb ik altijd dus een plaatje van het Nederlands elftal, sorry. Ja. Maar dan doe ik het voorbeeld van, nou stel je voor dat Frenkie de Jong na de wedstrijd, kennen jullie Frenkie de Jong? Vingers? Ja, oké, wel. Nou. En dat hij dan geïnterviewd wordt en dat dan iemand vraagt, wie was eigenlijk die man in dat groene pakje die tussen die witte palen daar achterin stond? Ja, dat zou een hele bizarre vraag zijn. Iedereen, natuurlijk weet hij wie zijn keeper is en wat hij staat te doen. En ik denk dat het niet ver van de waarheid is dat wij het onderling vaak niet van elkaar weten. Terwijl we echt in teamverband zouden moeten opereren. En als je dat wel van elkaar weet, wie wat zit te doen, dan kan je ook heel goed zeggen van oké, nou weet je wel, Michel is de komende 2 jaar even blue sky in ons team. Helemaal, ga maar lekker. Maar die en die en die zitten dit en dit op te lossen. En als team is dit onze communicatie en naar buiten toe. En zitten we de wereld ook wel direct een beetje beter te maken. Ik denk dat is een beetje mijn filosofie.
Ja, dus eigenlijk toch een klein beetje alles doen. Maar dan niet het schaap met de 5 poten, maar binnen een team.
Precies, ja, en zeker niet alles doen, want wij zitten in Nederland heel veel dingen gewoon dubbel naast elkaar te doen. Het is totaal niet efficiënt. Dus laten we ook een beetje afspreken. Die doet dat, die doet dat. Kijk, dat je af en toe iets repliceert van elkaar, dat is goede wetenschap. Maar dat je in Nederland, weet ik veel, 30 cohorten hebt die allemaal hetzelfde zitten te meten, dat vind ik niet handig. Dat hoeft gewoon helemaal niet.
Oké, dus samenvatting, de call for action is eigenlijk niet alleen blijven samenwerken en samen praten, maar ook verdeel een beetje het werk.
Ja, en organiseer het efficiënt. Want dan kun je met diezelfde pot geld dus veel meer doen. Veel meer nuttigs doen.
Weten mensen als Károly straks veel beter bij wie ze terecht moeten voor welke informatie.
Zo is het, ja.
Ik vind het een heel leuk gesprek. Ik zou zo nog wel een half uur door kunnen gaan, maar ik weet dat Eveline ook staat te trappelen om haar presentatie te geven. Ik wil jullie heel hartelijk bedanken voor vandaag. Ik vond het ontzettend leuk. En ik geloof dat Jana nog een bedankje heeft voor jullie.
Dankjewel.
Dankjewel. Voor het vervolgprogramma gaan we weer switchen naar het Engels om het over onze wetenschap te hebben. And our next speaker is our own Eveline Crone. She's a professor in developmental neuroscience in society at the Erasmus University in Rotterdam and developmental psychology at the University of Leiden. And today she will talk about growing up together.
Thank you, Michelle. Oh, that was a wonderful conversation just now. I really, really enjoyed it. So thank you, Michelle and Károly and Arne for that great, intermezzo, interchange. It was really wonderful. So my name is Eveline Crone. I work at Erasmus University and at Leiden University. And I'm now presenting the first English part of this afternoon. So welcome to those on the live stream who don't speak Dutch. Welcome to this scientific part of the symposium. And what I would like to do is to talk to you today about growing up together. And I would like to also discuss a little bit the possibility of whether we need also to think about possibly a paradigm shift or a paradigm change in how we approach our science, how we do our discoveries, and what can be also the impact of our findings at multiple levels, so both societal and scientific. So that's what I would like to discuss today with you. So when we talk about growing up, we often talk about how an individual, for example, here's a nice example of Boyhood and the movie 12 Years in the Making, how an individual progresses through various milestones in development from birth until young adulthood. And we value longitudinal data, and we value the very precise measurement of different processes that change while you grow up. But growing up is something that we don't do alone, individually. We grow up with people around us. We grow up together. And one of the important challenges for our field or how we approach our science is to make sure that we keep having this broader perspective, that an individual is an individual based on interactions with others, and that possibly certain individual characteristics can change when you interact with other people. So we need to incorporate also that dynamic part of growing up in our work. But we don't only grow up together, but we also grow up in a very complex society. Here's an example of young people going out on the street to protest for climate change notification by the governments, and they demand a change. And I could give, just as Michelle just also already showed, I could give many examples of large societal movements, geopolitical problems, wars that also come our way from all over the world, and now also in Europe. So people grow up individually, people grow up together, but people also grow up in a certain societal environment. And how can we capture that kind of complicated picture? How can we capture also all these collectivist forces that are among us and that also influence how young people develop? So a quote that I would like to make today is from the WHO, UNICEF, Lancet Commission, and they argue that scientific evidence in itself is not enough, but knowledge must be transferred into strategical, political, and social action. Now, you can debate about whether you agree with me or not, but to me this was a very inspiring quote, because it shows to me that we have an obligation as scientists to, of course, make sure that we build knowledge that is reproducible, that is valid, that is something that we can trust, but also that knowledge, that scientific knowledge, actually finds its place in the society around us. So for me, a personal ambition is to think about how to bridge that knowledge base that we acquire in our labs, in our experiments, with these big societal forces around us. And I would just like to give you an example of kind of the dynamics when you try to bridge these different knowledge fields. So, for example, if we want to think about societal impact, so that we have impact with our work in the society, that we use also knowledge from society, and that we kind of bridge that individual-based approach with these larger societal questions, then we can do that in multiple ways. For example, we can try to understand the societal dynamics better through youth panels, for example. So reach out to the young people that we investigate and find out how they see the problems that we try to understand. So bridging those two views can possibly lead to a better understanding, an understanding of the problem that we try to tackle in the first place. But it's also possible that those youth panels may help us also to shape our behavioral experiments, so that eventually we try to optimize the behavioral change that we think is important. And on the bridge of this societal impact and these behavioral experiments is possibly room to tackle big societal challenges. So the challenges that we face, if we can design experiments that possibly change certain aspects in the way we study behavior, then that may help us to also really target those societal questions that we're interested in. And I would like to give you an example, 2 examples actually. One of the combination between societal impact and youth panels, the way we try to approach it in my lab, specifically in the last 2 years, and see if we can learn from young people what they find important. And the second example that I would like to give is at the bridge of societal impact and behavioral experiments, where we design our experiments based on questions that arise in society. So let me start with the first example. And this is an example of a youth panel that was led by Suzanne van der Groep and Renske van der Kruijsen. They're also both here. And more people in my lab are working on these specific topics, but you will see them in this movie, where they went out to Rotterdam South, a neighborhood where young people live who usually do not take part in our scientific studies because they have no knowledge about it or because there's not necessarily the trust to participate in scientific research. And it's those young people that they try to approach. So let me show you an example.
Vandaag zijn we gaan sparren over de coronacrisis en de jongeren eigenlijk. En hoe ze daarnaar kijken en hoe we dat eventueel kunnen verbeteren in deze moeilijke tijd.
Ik vind het heel erg belangrijk om als jongeren mee te denken, ja. Ik vind dat zeer belangrijk, want ouderen die mogen wel dingen zeggen en die hebben natuurlijk wel veel dingen te zeggen, maar wat zij willen, dat is toch iets anders wat wij willen.
Stel nou, je bent even de baas van Nederland. Wat zou jij dan adviseren? Wat zeg je eigenlijk wat er echt moet gebeuren voor jongeren?
Zoveel mogelijk rechtvaardig te blijven handelen van zowel ons als normale mensen als de ambtenaren en de regering.
Ik hoop dat school beter geregeld is, want ik vind online les niet zo handig. Het is best wel chaotisch. Maar ik dacht dat ik misschien het enigste was die een beetje te veel aan het zeuren was, maar meerdere mensen zijn het wel met mij eens.
En het is ook gewoon fijn om te horen dat de anderen ook tegen dezelfde minpunten kijken, maar ook weer dezelfde positieve kanten zien.
Dat ze hun vragen vooral kunnen uiten en dat ze misschien daarmee wat kunnen doen en dat ze daarmee toch wel stappen kunnen maken.
Mee te blijven denken en communiceren over hoe deze regels toch zowel jongerenvriendelijk zijn als mensvriendelijk.
Okay, so here you see that these youth panels shaped us in our thinking of what are the problems that young people encounter and how can we maybe use that knowledge and try to find ways to make it more impactful in our scientific studies. And what was discovered in those youth panels is that these young people also expressed a strong need to contribute, to help, and to be seen. So we became interested in the question, do those experiences of pro-social helping, the possibility to help others, do they also relate to how willing we are to share some of our resources with others? And this is work by Sophie Swijen, including also a big group of scientists in the lab. And what she studied is on a daily basis the number of experiences that young people had with helping others, family members and friends. And she wanted to understand if that possibly predicted how much young people were willing to give away in a dictator game. And she shaped the targets of a dictator game in such a way that people could give away something to a peer that they did not know. And as you can see, those are the lowest values in pink because people don't share that much with someone else that they don't know. The second target was a friend, that is displayed in green, and it turned out that young people give more to their friends relative to peers that they don't know. But the biggest differences was in terms of how much young people were willing to give to a COVID-19 patient, a doctor in a hospital, or someone with a poor immune system. And it turns out that young people, adolescents, were willing to give away much of their resources to those individuals. but they gave away more when they had more pro-social experiences on a daily basis. So if on a daily basis they had more opportunities to help others, they were also more willing to share their resources with others. So for us, this was an important finding showing that it speaks against this idea of young people only focusing on the needs of themselves, but they are actively involved with the well-being of other people in society. Now let me give you a second example. So I showed you an example of how to bridge these different measurement levels. But another way we try to approach this in the lab is but not by using youth panels, but really diving into mechanisms. And here I'm talking about the interchange between brain science and behavioral experiments. And this is where we try to focus on what are the replicable consistent and robust findings that we can observe in an experimental context. And often those mechanisms cannot be directly applied in societal context. For example, in my experience, the biggest benefit of bridging brain science and society is in terms of science communication, where based on brain science, we have important, interesting discoveries that we share with society. But I don't have many examples of where directly we can use insights from brain science in society. However, if we go through the process of the mechanisms and target our behavioral experiments in such a way that we can develop interventions, this is then where the mechanisms can help us to develop interventions that can eventually speak to societal challenges. So as you can see, it's quite complex of how you can bridge those levels, but we don't shy away from complexity as scientists. So one of the questions that we had in terms of finding those mechanisms was, are there sensitive windows for pro-social and societal engagements? So now we go into this very detailed level where we really want to understand in smaller groups of participants the mechanisms behind pro-social actions, so actions targeted at the well-being of other people. To do that, we make use of brain science, and specifically in my lab we use fMRI, functional magnetic resonance imaging, to understand how certain regions in the brain are active when you perform a certain task. For example, prior research in brain imaging has shown that young people show an increase in risk-taking behavior and sensation-seeking, and that this is related to activation in the reward and control regions of the brain. We also see that young people show a change in friendships and peer relations, and that this is associated with changes in the social structures of the brain. So if we look at these changes in brain development, so this is work by Marieke Bos and by Lara Wieringa, who are also here today, what they have discovered over multiple years and using multiple data sets from various countries is that there is a second window of structural brain development between the ages of 10 and 25. So the first window is kind of the building of the brain, and the second window is this efficiency gain of neural development. And what they also discovered is that the shapes of development differ between individuals who are, for example, low or high on depressive symptoms, with those who are high on depressive symptoms showing a faster acceleration of brain development. So this made us think that possibly this window of ages 10 to 25 is a very important window to investigate, because it may be a formative phase in your development. So I'm going to show you a couple of experiments where we try to really dive into this mechanism by understanding reward sensitivity in the brain. So here you see an example of a study, an experiment, very detailed, controlled in the lab, where people could gamble between gaining the possibility of €3 or losing the possibility of possibly losing €3. And what we found is then when people gain €3, they show increased activity in a reward center of the brain. This is the ventral striatum displayed here. It's a very deep subcortical region in the brain. In every study that we do with a reward task, we replicate this finding over and over and over again. We always show this robust activity in the ventral striatum. at the group level. Once we dive into the individual level, this is where it gets much more complicated. So really understanding how this neural activity correlates with individual characteristics is much more complicated. So here we see a graph of longitudinal data of participants between 10 and 27 years of age who performed this task twice, separated by 2 years, and we see when you squeeze your eyes a nice quadratic trend of neural activity showing heightened activity in mid-adolescence. But if you look carefully at the graph, you see also that there's a lot of individual variation. Now the important question is this variation that we can explain or is it partly noise? Well, some of the variation we can explain. For example, here you see an example of levels of testosterone showing a rapid increase in levels of testosterone in boys, somewhat smaller in girls. And it turns out that this rise in testosterone partly explains the individual variation in activity in this reward center of the brain. So we thought we're onto something. Then we wanted to understand if this is a neural system that is active when you gain money for yourself, does it possibly also fire when you gain something for someone else? So in this experiment, participants played the same gambling task for themselves, their best friend, and someone they disliked. And the person that they disliked just gave them a very bad financial offer. Afterwards, we asked participants, how much did you enjoy winning for yourself, for your friend, and for the other person, and how much did you enjoy losing for yourself, your friend, and the other person? As you can see, people enjoy winning for themselves, they don't enjoy losing for themselves, the same pattern for the friend, and for the antagonist, it is reversed. People slightly enjoy losing more for someone who just gave you a bad financial offer. Then if we look at neural activity, we see that this pattern is exactly the same. So again, neural activity in the ventral striatum is higher when you win for yourself relative to losing for yourself, when you win for your friend relative to losing for your friend, but for the antagonist it is reversed. So this made us conclude that possibly this region of the brain can help us to understand the subjective pleasure of gaining something for yourself and someone else. So here you see again an example of a longitudinal data set, this time 3 measurements, showing this peak in neural activation when individuals gain for themselves. If we investigate this for the best friend, we also see this quadratic pattern, but only for friends who are very close to you, not for friends who change on a daily basis. And finally, also for the mother, this is cross-sectional data, and not longitudinal. We see this quadratic trend showing that individuals show higher activity in mid-adolescence when they gain for their mother. So it seems that for close others, we see the same pattern in these various studies. Now, close others are important, but distant others are possibly more important, especially in complicated times as what we live in today. So here we look at activity in the ventral striatum when you gain or lose, or gain or not gain for a charity. So individuals could choose their own charity and could either gain only for themselves and nothing for charity, for themselves and charity, so both a gain or only for charity. And we reference that to a condition where there's no gain for either party. It turns out that individuals show activity in the ventral striatum when they win for themselves, but not when they don't win. Also when they gain for both parties, but we don't see this pattern only for the charity. So this may indicate that for a distant other, even if it's important to you, such as a charity, we don't see that general pattern of reward feelings in the brain. However, if we then correlate it with individual differences in donation behavior, those people who are willing to also give to the charity, it turns out that those people who give more to charity also show more activities in this reward center. The same for self-reported level of perspective taking. Those higher on perspective taking give more to show more activity in this reward center during giving to charity. Finally, this is again a behavioral example of a cooperation again with close and distant others. In this cooperation task, a prisoner's dilemma task, people can choose between a benefit for themselves or a benefit also for the other. And what we see here in terms of development is that over time, individuals give more to their mother and their father, but for the stranger, it shows the reversed pattern. So we see an increase in in-group, out-group behavior over the course of adolescent development. Now, why am I showing you all these data? Well, I explained to you in the beginning, I want to talk to you a little bit about a possible paradigm shift in how we approach these studies. So I showed you here examples of different measurements levels: brain imaging, experiments, questionnaires, youth panels, and each of these measurements levels have their own advantages. For example, for brain imaging, it can provide us with novel perspectives that we did not think about before. Experiments can give us very controlled analysis. Questionnaires may lead to high generalizability because we can reach out to many people, whereas youth panels may help us to get ecological validity. But each of these measures also have their cons. For example, brain imaging may be low on generalizability, and experiments may sometimes lack ecological validity. Questionnaires may sometimes lack in providing novel perspectives, whereas youth panels, they may lack sometimes a controlled analysis. Now, if you look at this picture together, you can see that each of the measurements levels have their benefits and their disadvantages. And possibly the disadvantage of one method can be overcome by the advantage of the other measures. So that's why I would really try to make the case that if we look at a certain problem, that we really bridge all those different measurement levels and provide a richer kind of view on how we think are the ultimate conditions for young people to develop. Now, as I told you in the beginning, we're here also to celebrate the Leiden Consortium individual development. And let me just walk you through this before I give the floor to these fantastic young scientists who will present some of their work in flash talks. What is the Leiden Consortium individual development? It started in 2013. It was started by Marinus van IJzendoorn. He was one of the 6 co-applicants on the Gravitation Grant Consortium Individual Development. The main applicant is Chantal Kemner from Utrecht University. And in 2013, these 6 scientists started this project and asked all kinds of other scientists to join. I was one of the scientists who joined. Marjan Bakermans was one of the scientists who joined. And here in Leiden, we set up this study referred to as the Leiden Consortium Individual Development. Between 2013 and now, 50 young scientists and 150 students found their home in the project. So you can imagine we are very, very proud. We hope that after today, we will keep on building an open science database, and also when the project ends next year, we hope we can continue with our curiosity-driven science approach and adapt to societal challenges. Now, why the Leiden Consortium Individual Development? I explained in the beginning that there's possibly 2 windows of brain change: an early rise in building the brain and a second phase where the brain becomes more efficient. And we hypothesized that possibly these periods of a high change in brain development may be windows in development with higher sensitivity to the environment and possibly differential susceptibility to the environment, because not everybody responds to the environment in the same way. To test this question, we developed this multiple cohort study, 2 cohorts, an early childhood cohort and a middle childhood cohort. And the interesting thing is that at the second, in between this second and the third year, there was an intervention, both in the early childhood cohort and in the middle childhood cohort. The other nice thing is that the cohorts partly overlap. So at age 7 and 9 and 8 and 10, there's an overlap between the first 2 measurements of the middle childhood cohort and the last 2 measurements of the early childhood cohort. And that way we can hope we can really follow this whole trajectory. As you can see, there's also a focus on both home visit and brain science methods. So in that sense, in this project, we really try to embrace this complexity of the various measurements. There's also an additional phase in this project, and that is that the pandemic hit also this specific project. So we have opportunities to examine the effects, but of course it was also a big setback also for the scientists who did an amazing job in terms of resilience and getting the project back on track. I'm so proud of you all. So several compelling questions that we can answer in this study. For example, related to the design of development, of genetic modeling, because half of the participants are monozygotic twins and half are dizygotic twins. We have, well, I'm going to go a little bit faster because you can see here all these different problems that we want to attack in this specific study. Now, before I give the floor to the amazing scientists, let me just go back to a quote that Michelle also started with, and that is, even though we want to embrace this complexity and we want to speak to societal challenges, the history of science has shown that many of the great breakthroughs resulting from scientific research were regarded as significant only in hindsight. They were not the result of a focused effort to achieve a specific impact, but instead reflected serendipity. I think we should embrace that as well and make sure that scientists always keep the freedom to pursue their own ideas, because scientists are part of society, they care about society, and I would like to argue against very focused programs where we have to solve specific problems, but to really have the scientific freedom to tackle these problems as good as we can. So, meet our L-CID scientists. We will hear flash talks. Unfortunately, Mara van der Meulen is sick. She's at home, so we won't hear her flash talk. She is, huh? Okay, yeah. I thought maybe miraculously she showed up. But Mara, I think you are watching from home. We miss you, but we completely understand, and there will be multiple other opportunities to meet Mara in the future. But we also have Michelle Achterberg, Simone Dobbelaar, Jana Runsen, and Lina van Drunen, who will now take the floor and present their flash talks. To have this support, like my backup. So. Thank you, Eveline, for this lovely keynote that also gave us a really nice introduction to our flash talks, because we want to present our newest findings, but we want to do it fast. So it's nice that Eveline already explained our quite unique but also difficult design. So I want to talk about middle childhood, so the middle childhood cohort. And why I find this the most interesting time is because this is really the time where friendships emerge, where they truly develop, where children need to develop and maintain social relations. And in order to do that, they also need to handle social situations, social feedback, but also social rejection. And some children, they are pretty good at that. So if they get rejected on the playground, they just shrug, they keep their head high, and they move on. But not all children manage to do so. Some get really angry, frustrated, or even start to use reactive aggression. And I found it very interesting to see what makes it that some children are fine in these situations, while others have more difficulties with this. And that's why I am interested in the nature, the nurture, and the neuromechanisms of social emotion regulation. And in my research, I studied this using an experimental design, and that is the social network aggression task. So in this task, there are actually two events. And prior to the lab visit, where we do this task in an MRI scanner, we ask the children to fill in a personal profile with, for example, questions such as, what is your biggest wish? During the scan, they get feedback from unknown peers, which could be either positive, neutral, or negative.
after they receive the feedback, they get the opportunity to react towards their peer. And they can do that by blasting a loud noise. And they can choose whether they want to have a short, soft sound or a very long and nasty sound. So over the course of my PhD studies, we did this experiment over and over. And what we actually see is that in multiple samples over different ages, aggression leads to, or negative feedback leads to the most aggression. So we first studied this in young adults, where we saw large differences between positive, neutral, and negative feedback. But also in several samples, we did a pilot sample of 7 and 8-year-olds, a test sample, replication sample, a twin sample of over 300 children, and also on 9 and 11-year-old children, we saw that negative feedback leads to aggression. So, as a neuroscientist, I'm also interested in what happens in the brain. So, if we look at the brain and we study neural networks that are actually associated with this aggressive behavior, with the difference between neutral and negative feedback, we see that these brain areas light up, the dorsolateral prefrontal cortex, bilaterally. And what we actually see is, if we look at the association, that the more activation you have in these regions during that noise, during the social evaluation feedback, the less aggressive they actually are. So more DOPFC activation leads to less aggression. Well, for a neuroscientist, it's pretty cool to find brain behavior associations at the whole brain level. But there's also, more importantly, we showed that over time, if we look at the development, we see that the children that have the largest increase in DOPFC activity across 2 years, so from 7 to 9, those are also the children that showed the largest decreases in aggression after rejection. So, stronger DOPFC development leads to larger decreases in aggression. And this actually shows that what I hope you are already kind of convinced about is that development does matter. Well, Eveline already mentioned it. We have a twin study, so that's pretty unique as well. And therefore, we could also look at the genetic and environmental aspects of behavioral aggression and brain activation. So what we found is that for behavioral aggression, if we look at the variation, then we see that approximately 10% is explained by heritability, and 8% or so is explained by shared environmental factors, so for example, parenting. And the largest part, or the rest, is explained by unique environmental factors and also measurement noise. Also, if we look at the brain, we see a similar pattern where approximately 14% is explained by heritability, but the largest part is explained by unique environmental factors and measurement error. So what we actually see is that the variation in aggression and brain activation is explained by both heritability, but also there's a lot of room for environmental influences. So as I already mentioned, we see that development matters, and by looking at these environmental influences, the neural mechanisms, we can actually investigate, but ultimately create these optimal conditions for each child to reach their full potential. Thank you.
Hello everyone, my name is Simone Dobbelaar and I'm very happy to tell you something about the study that I've been working on the development of responses to social feedback in childhood. And first I'd like to thank my co-author team of Michelle Achterberg, Lina, Anna van Duivenvoorde, Marines van IJsendoorn and Eveline Crone. So we've already heard a lot about childhood and middle childhood, and that's the period that spans approximately 7 to 10 years of age. And it's an important period because children start to experience more social situations and social evaluations in these situations. And it's also important to learn to adapt your behavior to these social evaluations. So for example, positive evaluations can lead to pro-social behavior, such as helping, whereas Michelle just explained that negative evaluations can also lead to frustration or aggressive responses. But what happens in the brain during these responses is still relatively unknown, even though this is such an important period for the development of these behaviors. So therefore, the first aim of our study was to investigate neural activation during responses to social feedback in childhood. But Eveline also just explained the really nice design of the L-CID study, and we wanted to use that in our advantage to also examine replicability of neural activity in childhood. So here is the design again, and as you can see, there are 2 time points that overlap in age, and we use this as an independent test sample and an independent replication sample. And the test sample consisted of 385 participants with MRI data, the replication sample of 195 participants, approximately half of them were girls, and they were on average 8 years old. So participants performed the social network aggression task. Thank you, Michelle, for already explaining the task. So participants received either positive, neutral, or negative feedback, and then had the opportunity to send a noise blast towards that peer who gave the feedback. And for this study, we were specifically interested in what happens in the brain during this noise blast event. So our fMRI results show that the medial prefrontal regions of the brain were specifically activated following both positive and negative feedback. So possibly these regions are specifically important or respond to events that are socially salient, so either positive or negative. But on the other hand, the more lateral prefrontal regions showed most activation following positive feedback. And participants were instructed to always send a noise blast. So we suggest that these regions might be important for inhibiting responses, because you might be less willing to respond aggressively when you've just received positive feedback. And which I think is a really nice finding, is that we found these patterns relatively robustly over the 2 samples. But to really investigate whether indeed these regions might be important for inhibitory processes, we looked at the brain-behavior relation, and we found that activation in the dorsolateral prefrontal cortex during this noise blast event, so when you respond to feedback, was associated with noise blast duration. So participants who had more activation were less aggressively, responded less aggressively. So we found this result actually irrespective of the type of feedback that they received. So we suggest that indeed these regions are important for inhibitory processes. So together, we believe that these findings support a neural basis for social regulatory mechanisms that is already present in childhood. And this might help us understand why some children are more prone to aggression than others. Thank you.
Oh, wow. It's the first time for 2 years, so I'm really nervous. No. Hi, I'm Jana, and I'm not going to talk about the brain or aggression, so be prepared for a topic switch. I think you heard from Eveline that we also did an intervention in those 2 cohorts, and that's what I'm going to talk about today, about the 2 randomized controlled trials with the video feedback intervention to promote positive parenting and sensitive discipline. And we did that in the parents of the 2 cohorts of twins. So I think, well, many researchers in child development know that parenting does matter and is important. And we know that parental sensitivity is related to positive outcomes for the child. For example, better social competence, better cognitive outcomes. And we also know that harsh or insensitive parenting is related to negative child outcomes. For example, worse executive functioning or more substance use problems. So therefore, the video feedback intervention is aimed at fostering positive parenting and sensitive discipline in parents to, indeed also help the children in the long term. And the intervention is based on the attachment theory and also the social learning theory, and it's based on video feedback. So the interaction between parent and child are videotaped, and positive moments are used to give feedback to the parent to encourage positive behaviors. It consists of 5 sessions in which different themes are tackled. So a recent meta-analysis on 25 randomized controlled trials by Van Eysendorn et al., thank you, Rien, that found that the WIP-SD is indeed effective in promoting sensitive parenting, a sensitive attitude of the parents, also child attachment and child externalizing behavior, or less externalizing behavior. So we know already that the intervention is a very good intervention and is very effective. But all those studies have been done in young children up to 3 years of age. And we wanted to know, does it also work in older children? Because early interventions are not always possible, or some problems don't evolve until a later age. And also we didn't know, does it also work in parents of twins? Having a twin is, of course, a bit more complicated than just having one child that wants your attention. So that's what we wanted to test in our study. So you know already there are 2 cohorts. We had the early childhood cohort. Children were about 4 years old when we did the first measurement. And the middle childhood cohort when children were 8 years old. So this was at the first measurement. They were about 2 years older when the intervention happened. So quite some years later on compared to earlier studies. We did 2 pre-measurements where we observed parental sensitivity and sensitive discipline. And in the middle childhood cohort, we also assessed the attitudes towards sensitivity and sensitive discipline in the parents. Then we conducted the intervention. Well, as I said, it was a randomized controlled trial, so it was blind. The researchers, or I did not know which families were in which condition. And afterwards, we measured again the same measurements. So what did we find? In the early childhood cohort, my colleagues found that it was successful in changing or increasing sensitive disciplines in the parents in the intervention group, and you see that it continued to decrease in the control group, but it stopped to decrease and it even increased in the intervention group. But we did not find an effect on parental sensitivity. And in the middle childhood cohort, we found an effect on the attitudes towards sensitivity. As you can see, after the intervention, the attitudes of parents in the intervention group increased much stronger compared to the control group. But we did not find an effect on observed sensitivity or sensitive discipline. So what does it mean, to sum it up? We did not find an effect on sensitivity in both cohorts. So one explanation might be that there is an age limit for the WIP-SD as it is right now, or that there is a sleeper effect, that it just takes some more time, so we have to measure again a year later or 2 years later to see change in behavior in parents who have been behaving in a certain way for a longer period of time. Basically the same is true for sensitive discipline, which we found in the early childhood cohort, but not in the middle childhood cohort. It might be limited to preschool children, or of course, it could also be a sleeper effect, so it just takes some more time. And the last finding is an indication for that, because we found that the attitudes had already changed, but behavior hadn't. So maybe for those parents, it just takes a longer time to translate the attitudes into real behavior. And it could also be possible that they need some more sessions to really change the behavior. But that is something that we want to find out in the future. So thanks a lot for your attention.
So I'm the final one. Welcome everyone, my name is Lina van Drunen and today I will talk a little bit more about how music alters brain development, or it may alter brain development. So the human brain goes through a period of dynamic changes between childhood and early adulthood. We already know that there's a decrease in grey matter going on. We also call this the maturation. Yet it is currently unknown whether these developmental patterns that we see are indicative of sensitive windows, where experiences would have hidden effects on brain developmental patterns. One example of an environmental factor, One example of an environmental factor influencing these brain developmental patterns might be musical capability. And in musical capability there are lots of individual differences because only a minority of individuals become musical experts, such as the Beatles. Come together right now over me. So the Beatles didn't become experts because they practiced a lot and they probably had some genetic predisposition as well. But also they probably started having musical experiences very early in life. And this can also cause individual variability. Therefore, studying how musical capability relates to brain development offers us a unique opportunity to investigate the genetic and environmental factors on brain plasticity. So to tell you a bit more how we measure music, we measure music with sensory motor synchronization, and it's defined as the ability to synchronize movements with predictable events, such as a beat. And these designs are often used in musical capability paradigms. So when playing music, one specifically needs to synchronize their movements to a predicted beat. So this depends on specific regions in the brain. And two networks are especially important. And regions involved in these networks are the frontal lobe. This is important for the preparation for motor skills, for example. The basal ganglia and the limbic system, which is important for the emotional processes or for memory reformation. The cerebellum, of course, for the fine motor learning. And the temporal lobe, important also for auditory processing, but also for prediction of the beat. So all these regions are involved with music. So it's, that's what I wanted to do. Therefore, I'm very curious whether there are individual differences in these brain developmental patterns can predict how good they are in this specific music measurements, SMS skills. And as a second aim, we also want to test whether the relation between sensory motor synchronization and brain development is influenced by genetic or environmental factors. However, I did not analyze this, so I will not explain this further on in the next slides. Well, as you already saw on the previous slides of my colleagues, I will include 3 brain measures of MRI data and 1 time point of sensory motor synchronization. And during the SMS paradigm, participants were asked to tap the exact same tempo as the metronome or alternately tempo to the metronome. And in the final part, we asked the participant to tap along with 4 different kinds of music songs. And one example of a music song is this one. Bruises on both my knees for you, don't say thank you. And we operationalized sensory motor synchronization by computing how stable participants were tapping on the beat. What I already can show you are some of my behavior results. As you can see on the y-axis, you can see how stable the children were tapping, and 1 is very stable and 0 is not that stable. And on the x-axis on the left, I divided the sample in early onsetters, late onsetters, and no onsetters in musical experience. And late onsetters are the ones that had musical training after the age of 7. And on the right, you can see how responsive they were to music. And taken together, it appears that how stable children tap on the song that I measured depends on their musical experience in their life, but also how responsive they are to music, which is a bit interesting, I think. For our neural results, I can already show some first aims, because it's quite a difficult analysis, but I will walk you through. Because the first aim of the neural results was to identify classes in brain development, using a latent class growth analysis in M+. And first, the model should be terminated normally before we can test whether these class memberships are also predictive of sensory motor synchronization skills. So this is nice. Something that I can show you is that we see some classes in brain development, for example, for hippocampus development. As you can see, they mostly differ in intercept, but I have to say that the upper two classes compared to the lowest class is different in slope as well. The upper two classes are negative and the one below is positive. So it is interesting to check whether this has an impact on how good they are in music. However, we also checked with the latent growth analyses. If it was not possible to identify classes, we had to check whether there was one latent growth going on. And that was, for example, for the, the inferior parietal region. We could not identify classes, therefore we ran a latent growth analysis. And with this analysis, we can check whether intercept or slope is more predictive for sensory motor synchronization. So it's a different question, but I still want to check both analyses because maybe there's some information about it, about sensory motor synchronization. But how these neural data relates to musical skills is still something that we really need to dive into and really need to explore before I can present you the real results. But it's very interesting, and so stay tuned for the rest of the results, of course. Thank you very much. If you want to know some more, you can always find me on this email. You can also Twitter me. And if you're very interested in a topic, you can also read my pre-registration online on OSF. Thank you very much.
Thank you, ladies, for these 4 awesome talks. Super exciting science. We have a few minutes for questions in case there are any for one of our specific speakers or the program in more general. Marika?
Okay. Yes. Let's do it again. Thank you all for your nice talks. And I'm always interested in this music development, not on a scientific level, but on a personal level. And what we discussed earlier actually is how we can make a paradigm shift. And I think that what you presented was something that can be related to each other, given that it's a quite task which is related to real life, let's say it in that sense, but also on the other hand, it is really brain development. So what do you think that your study, if you are completely analyzed it, how it could bridge this gap or can be translated already?
To society, you mean?
Yes.
Yeah, well, of course, I'm mainly interested in how brain development occurs and whether it's a sensitive period for other environmental factors that can impact brain development. So that is the first thing I just wanted to know. It's a fundamental question, I think. But since music is so much involved in every brain region, and it's also much related to how good they are in language, but also sometimes in math skills. It's not only just music, but also sporting skills. It's all connected to being, musically well, musically good. So I think that my question, I will answer a fundamental question, but I can give back to society that, for example, if we see that the development is slowly decreasing instead of accelerated decreasing, then we can maybe suggestively say that the development is going on longer than for the individuals that had musical experience than for the children that didn't have musical experiences. So they have a wider opportunity for brain development. That will be very nice if I can, of course, present you that, but that might be an idea that I can give back to society.
Yeah, because I was even thinking more concrete, is that if we look at the discussion between Károly Illy and Arne Popma and about how our youth is now developing and have a lot of stress, and if we look at how the schools are currently organized, then we see there's no much room anymore for music or for sports activities.
Yes.
Or if they have to do it, it has to be on the most highest level ever, and it's quite stressful again. So, well, there I think there would be a really nice.
Yes, interesting to talk with teachers and to bring it back into their school programs again. Yeah,
there we can go. Yeah, thank you.
That will be nice.
Other questions? Yeah, Neeltje? The microphone is coming.
Yeah, I think, so first of all, thank you all for these great talks, really inspiring. I think my question relates a bit to Marike's question. So my parents are both music teachers, and what they keep telling me is their group, I guess, of students becomes more narrow and narrow, and that nowadays music lessons, particularly individual lessons, are more and more reserved for the high SES individuals. And I was wondering if you could tell me a little bit about how that is in your sample. Do a lot of children have music lessons? And we're talking about opportunities and the window of sensitivity. Do you think that that might change through the years? And how can we foster that window of opportunity for that specific developmental skill, I guess? Because I believe that musical development, obviously, is really important.
Yes, I think SES is very much related to musical experience. In my sample, it's actually relatable to a population, to a large population. I think around 20%, if I'm correct, was able to experience music before the age of 7. And after the age of 7, when they got a little bit older, around 40%, I think. But it is very difficult to say how good they were. Of course, I can measure it with the task, but how good they were in an instrument, it's difficult to say. So we have a questionnaire that also asks about their retrospective musical experience. And the question was, how can we improve it so that the people with lower SES can also be...
Yeah, because I guess we heard a lot about including youth panels and including all people from all walks of life. How could we, do you have any ideas how to foster that, maybe?
It's maybe a little bit relatable to the question of Marieke. So it should come back into the school programs where everyone can have the opportunity to learn a music instrument. And perhaps school can, if they see a talent in someone, maybe they can really help them improve in that instrument or provide more extended lessons, for example. I think music is such an important part in development, but teachers also have to see that, and maybe we have to tell teachers that it has to be incorporated in their program as well. Yes,
I think that is also something that is very important, and also a good example from you is that you show with these fundamental developmental science actually have something to show teachers to prove that it really is important to invest in those I don't know the English word, vakdocenten, really focused on music. And also, if we want to invest a lot of in prevention, then maybe we don't need the specific rots and water trainings, but we can just have simple music lessons within our classes, and that might be enough to foster the window of opportunity. Yes. So I do think.
Thanks. I think my parents would agree, so thanks.
Okay, great. So, well, music is important, but coffee and some nice goodies is as well. I hope this already gave you some nice food for thought. We're going to take a coffee break, and after the break, we will have our fantastic keynote speaker, Rogier, present. And at the end of the second session of this afternoon, Lara will have a special treat with a lookout for these studies in the future. So stay tuned, and more to come. Enjoy coffee.
Welcome in the last part of today. We have a number of exciting items in front of us, and we will first start with a little surprise. Over the past decade of running the Leiden-CID study, we had numerous fruitful collaborations with developmental neuroscientists around the globe, and some of our esteemed collaborators shared their valuable, insightful views about the L-CID study in this short video.
What are your experiences with the L-CID study?
So to me, the L-CID is one of those really rare data sets that seems to turn the dial in scientific innovation. It's a large, very dedicated effort to characterizing human behavioral and brain development. The study is comprehensive. It's large, it's multimodal, it's longitudinal, it includes a twin design and an early intervention. And you really don't see that combination of those aspects in many data sets today, especially not one as large as L-CID. And importantly, the large sample size allows us to assess the robustness of any observed effects, which you can't do with many data sets that include human subjects, especially developing samples.
What opportunities do you see for L-CID in science?
One thing that makes me excited about the project is that it includes both twins and longitudinal data. So with this combination, researchers will be allowed to look at both genetic and environmental effects on how the individual differences in brain development over time in kids. And this combination is really rare in science, so it's a really exciting opportunity.
This design, I think, would be a really great exemplar for other countries to maybe look to and hopefully adopt at least some aspects to see if something similar can be done in the United States or elsewhere. So that's already a big impact as an exemplar study. I think you have worked to make your data, it seems like, available and accessible. And so that's already, again, a very big thing that doesn't often happen in large studies, but seems to be more the norm these days. And so I think that will be really useful. But also just the amount of work that's been put into making the scientific findings accessible to a broader audience. So not just the scientists, but to other relevant stakeholders, including young people. I really enjoyed that video that defined the 5 brain facts in the house. I thought that was just a really clever way to disseminate the research.
Most adolescents don't become clinical or developmental psychologists, and most of them don't become neuroscientists. So asking them what their lives are like is important. And I think driving that forward, developing the methods around that, developing standards around that, really thinking how to do that work is going to be really profoundly useful for our field, not just for people who are doing usual straight up developmental cognitive neuroscience, but especially also for people who are studying a really wide range of populations and a sort of more representative samples. So.
What opportunities do you see for L-CID in society?
I think parents are really curious to see what they can do in order to help nurture their children and to contribute to optimal developmental trajectories. And so having this intervention component embedded in a longitudinal neuroimaging and cognitive assessments, I think is going to be really helpful.
The open science approach of the L-CID investigators affords us the potential to harmonize or link up with data sets that are curated in other countries and in other cultures. And so one really important example of this relates to how children have been faring through the COVID-19 pandemic. So comparing the findings, for example, in the L-CID to those, say, in the US, where lockdown policies may have varied, can really provide deeper insights into policies and decision-making that can inform future policies and decision-making. And so now the children are entering mid-adolescence. And so the time is ripe to continue to follow this unique sample into this critical developmental transition into adolescence when individuals are becoming more independent. And we know that adolescence is a period of great individual growth, as well as significant risk for mental health difficulties. So with the L-CID, we could have lifetime deep and thorough characterizations of these individuals, which is really needed for identifying those individuals at greatest risk, as well as contributing to our general scientific knowledge of how you construct a brain. So in other words, child and adolescent brain development is really one of the last frontiers of science. And the L-CID dataset allows us to begin to ask really exciting questions about how we all develop.
So knowledge about both physical environmental factors and social environmental factors is important also for policymakers, I think, and for society at large, because this can inform what we need to focus on and in order to optimize child development.
I just love how Professor Nim Tottenham calls it the L-CID. Don't you think so? It's really nice. Thank you, team, for putting this together. It's really wonderful. They interviewed all our collaborators. Thank you, Kate, Margaret, Christian, Nim, if you're watching, for all those really kind words. I'm Lara Wieringa, and I'm an assistant professor on the Leiden CID study, and I've been working on it for 4 years, and it's an amazing journey. And I'm your moderator of this afternoon session. For now, I'm very proud to introduce to you our keynote speaker, Rogier Kievit. He is a professor at the Donders Medical Institute of Neuroscience in Nijmegen, and we are very happy that he moved back to the Netherlands and continued his lab here. After his PhD at the University of Amsterdam, he moved to the UK, where he worked at the University of Cambridge as a postdoctoral researcher, and he studied what brain developmental changes underlie executive functioning at the Cambridge Center of Aging and Neuroscience. He started his own research group in 2050, where he applied innovative psychometric methods to better understand these individual differences in development of cognition in relation to dynamics of brain development. And he received many awards and grants over the course of his career, including a number of Rising Stars announcements. And he recently was awarded an ERC grant, starting grant, with which he will conduct a very ambitious project to study cognitive dynamics in children. So everyone in the field agrees that understanding individual differences and change are the next important steps in the field. Yet studying this is methodologically and conceptually challenging. But Professor Kievit is a real pioneer in applying methods to better understand what brain patterns may explain individual differences in cognition for both the under and above average performance. And you can imagine we were very enthusiastic to hear that he agreed to present his work here today. So I give you the floor on his talk about understanding the dynamics of neurocognitive development using theory-based models. Welcome.
Thank you very much. Can everybody hear me? Great. Well, it's wonderful to be here in 3D in real life for the first time in years. As much as I love my kind of kitchen and the chair that's sat beside it. So I'll be talking to you today about understanding the dynamics of cognitive development. And as Lara mentioned, we spent quite a long time in the UK, at the University of Cambridge, which is a lovely place, and it looks like you think it might. It has lots of lovely views, it has rowers, and occasionally you go for lunch and get unexpected guests, in which case a child comes in handy, so you can pretend to take a photograph of your child and not of Stephen Hawking, who sat down beside us. But we're also very glad we came back. And why did we come back? Well, many reasons. For one, that Cambridge became too dangerous for us as a family. There are row cows that moo at you. And there are lethal birds, lethal swans that will attack you in the streets. So you might think the Netherlands is a safe place compared to Cambridge. So we moved back to the Donders Institute in the summer of 2020, which is a lovely place. And one of the many things that's nice about it in the Netherlands is that it's so close to kind of everything. So you can visit all these kind of amazing groups, such as the groups here today. At the Donders Institute, I lead the Lifespan Cognitive Dynamics Lab with a wonderful team of researchers, some of whom have now gone on to bigger and better things. And we're interested in how and why cognitive abilities change across the lifespan. And to do that, we use model-based developmental cognitive neuroscience. So today, I hope to convince you that this is the single most exciting time yet to be in developmental cognitive neuroscience. And I don't mean the last 2 years you spent kind of at home working from home, I just mean in the field in general. And why do I say that? It's because the combination of new data and new models have opened up entirely new questions we could never ask before. And I would argue that for the first time since the inception of the field, we're now actually studying developmental cognitive neuroscience. And over the next 40 minutes or so, I hope to give you some insight into some of the tools we're using and some of the data sets we're using to answer what I think are exciting and new questions. So you can think of models as tools that you basically get from the garage if you need them. So you know what your question is, and you go and you grab the suitable tool. By models, I mean models such as structural equation models and linear mixed models and latent class analysis and factor analysis. And you've seen some of those today. So they have many practical benefits. They allow you to do dimension reduction. So you might measure brain structure or brain function across a large number of regions, or even all the voxels in the brain. So you might use factor analysis to reduce the dimensionality of your brain. Or you might use it to identify subgroups that differ on some characteristics. You might use these tools to do model comparison or to reduce measurement error. For instance, this is the longitudinal data from our Cambridge study on aging. This is the raw data, and this is what the data looked like after we applied factor analysis. You might use these models to do a better job of dealing with missing data. Or you might do it to do a better deal with correcting your standard errors, at which time most of you will start to slowly fall asleep. Entirely understandable. Now, I will excitedly talk about all these kind of slightly boring things in the pub, but I do agree that this is more of the kind of eat your vegetables side of using models. If they're good for you, you should use them, and you should feel slightly bad if you don't. But that's not what I'll be talking to you about today. Because I think models can be far more exciting, and I think a better way to think about them is as conceptual affordances, and I'll talk you through what I mean by that. And that's more the cake eating side of things rather than the vegetable eating side of things. So what are affordances? This is a term I've borrowed or stolen from the kind of perceptual motor literature. And it was Gibson who said, the world is perceived not only in terms of object shapes and spatial relationships, but also in terms of object possibilities for action. In other words, when we see objects in the world, we don't just see them, we see them as possibilities for action. We can do things to them or with them. For instance, you might see one of those large concrete kind of cylinders that you can either stand on or roll or get in. You might see a light switch or a doorknob, and it's almost impossible to see these objects without immediately imagining an action you can perform on it or you can do with it. And incidentally, it's not just humans who immediately certain objects invoke actions, animals do it too. So lots of objects in the world invoke these kind of possibilities for action. And I will argue that models offer the possibilities for inference. In other words, if you teach yourself these types of models, if you teach yourself what the parameters mean, they make you look at your data sets in new ways. So they make you kind of realize questions you didn't even know you had. So the old-fashioned way to think about models is that you already have your question, and then you decide which model should I use, which statistical tool should I use to answer the question I already had. And what I hope to convince you of today is that certain types of models can go a step beyond that, is that they can make you realize questions you didn't even know you had. So that's the model side of things. And the other side is data. So we need the data to kind of allow us to answer these questions. And on this side, I think this is one of the most kind of exciting times to be in the field because the newest data resources, and we've seen a few examples today, are phenotypically more diverse than they've ever been before. We now have data on social media use, on spatial navigation, even on typing speed. We have full genome and full exome sequencing of hundreds or thousands of children. The data is more precise. For instance, this is our kind of data from a collaboration with Cardiff, where we can use the Connectome scanner to directly measure the size of cells in the brain. It's temporally richer, so we can now measure a greater number of waves. We already heard about the L-CID study, but also finer resolution. We now have longitudinal data at the resolution of seconds or minutes, and different periods. This is data from the amazing developmental human connectome project, where they did prenatal imaging, so we can actually see the brain structure of a child even before it's born and as it develops. So you can see the cortex start to fold there. 10, 20 years ago, if you scanned 8 people, that would get you a Nature paper, and now we can scan babies before they're even born. It's truly a remarkable period to be in the field. But above all, the data sets are simply larger. And larger doesn't just mean that your p-value that was 0.053 is now 0.49 and makes you all happy. It means we can ask fundamentally new and different questions of our data. So just some of the data resources that are out there right now, obviously, first and foremost, the L-CID study. So as you can see, kind of the data will, I suspect, become available at some point, kind of using these wonderful FAIR principles. And there are many publicly available data sets that have new challenging properties and new phenotypes that you might not have ever thought about. There's, of course, the classic study, the ABCD, which has yearly measurements and is relatively easy to access. That allows us to study 12,000 children, and we've gotten used to it, but I did my PhD, and one of my first papers had 80 people, and that made people look at me like, oh, you have 80 images, and now we can just download data for 12,000 children for free. There's Koosje Veldkompis in the audience, I believe, who is kind of one of the data managers for the youth study, which is another wonderful project with longitudinal data that has imaging and lots of rich phenotypes, and as I learned today, even allows us to link up to CITO scores, so we can really make the link from societally relevant, kind of academically relevant scores to kind of our fundamental cognitive neuroscience. As of 2 days, 20th of March, I just saw this posted on Twitter, there's the StressNL database, which has kind of experimental data on stress in over 5,000 participants. Every single day, there's a new exciting resource out there. In the UK, there are large samples such as Understanding Society and the Millennium Cohort Study that have thousands and thousands of adolescents measured every year for a decade. But there's also school data. So many of the children in schools nowadays use one of many different kind of educational tools. One example is the Math Garden or the Rekentuin. It's a project from the University of Amsterdam originally that basically made arithmetic fun. So children can play these games and then they can win points, and children like to win points, which means they get up at 4 a.m. to win points, which means you can see these types of patterns. So this is the data from one child learning 4 times 6, or 6 times 4. So this is one child across a period of a little over a year who goes from guessing 6 times 4 to knowing he or she doesn't know what 6 times 4 is for about a year. And then they're like, I'm going to try. And they spend 20 seconds trying to get it right. And they don't quite get it right, but they know they're a bit closer. So then they spend a period of several weeks where it takes them up to 20 seconds to get the right answer. And then one day, it just clicks. And then for weeks, they basically make no more mistakes, and they only take a few seconds. So we can study this level of development. We've never been able to do that, which means we can now link that up to other development. What happens to this child in other types of sums linguistically? That sudden moment that this sum clicked, what else happened in that child? In fact, this data is so rich, and this is kind of even somewhat outdated. I think there are up to 2.5 billion sums of just children from the Netherlands. So you can see the school-level data here of their ability estimates. And here is the summer holiday. So you can literally see them decrease in their ability. And I would be the first to argue that the summer holiday is very much worth a small dip in your cognitive ability. But this is the level of resolution we can now study. And what I hope to see more in the future, and I suspect will be more common in the future, are these hybrid designs. So these are 400,000 children who've already done all of this. So the next time we start to, say, image children or do genetic sequencing, can we link this new data to the existing resources of their school-level data, of their years of data on these types of apps, learning to read, learning to write, learning to do arithmetic? So this is kind of such an exciting time to work in this field. But today we're going to be talking about why development matters. And for a long time, we haven't really done that, because for a long time we thought our job was to take the best possible snapshot we could of children or of people in our samples. So we worked on the best questionnaires, we worked on the best cognitive tests to measure our latent factors with the greatest fidelity. And that's exciting, but these snapshots miss the most fascinating dynamics, which unfold over time. So we need to move away from these high-resolution snapshots, and we need to study development and change as it occurs over time. So for the rest of the talk, I'll be focusing on how new models meet new data to answer new questions. And I'll be talking about two projects. Firstly, how can we measure cortical maturity at the individual level? And secondly, can we measure cognitive variability in development? So the first project has this catchy title, Towards a New Definition of Cortical Maturity, Evidence from a Unique 12-Wave Developmental Sample. And this is very much an example of team science. This is led by Dr. Delia Furman, who is now an assistant professor at King's College London, and a collaboration with our wonderful collaborators in Denmark. In this project, we wanted to understand brain development, and we've already seen some really nice examples earlier today. Because we know the brain changes continuously across the lifespan, starting in utero. And to give you an example, there's a lovely paper out there now as a preprint that has essentially developed these growth charts for the brain. That was unthinkable even 5 years ago. And I think the final sample is up to 120,000 individuals. And they've measured from prenatally, which you can see kind of on the left, all the way to old age. And then they looked at these different brain metrics to give us this normative curve of brain development so that we can then see what is atypical development, what does being above or below the curve tell us about your risk for neurodevelopmental disorders or for dementia. And we care about brain development because it's been associated with a range of lifespan outcomes we care about, including kind of mental health and physical health and all of those other factors. So we want to understand brain development. And a common metric in brain development is cortical thickness. It's a very developmentally sensitive metric, and we tend to find this pattern, and you've seen it a few times today, on nonlinear thinning, which starts in childhood between 6 and 9, and it goes on until late adolescence, around 25. And this change in cortical thickness is influenced by a lot of different processes, including dendritic shrinkage and spine loss, myelination, neurite branching, and the increase of more complex dendrites in human pyramidal neurons. So all of these things together play a role in cortical thickness, and they together affect this kind of interesting developmental trajectory. And there are many neurodevelopmental theories of brain change. And an especially popular concept is this idea of brain maturation or brain maturity. It was originally proposed in the early 90s by Dan Belsky, who argued that various factors probably affect the rate of maturation. In other words, what happens to you early on in life probably affects the rate at which you mature either more quickly or less quickly than you would otherwise. And this has spurred a lot of interest, and there's a nice kind of overview paper that argues that timing in brain maturation, whether accelerated or delayed, is assumed to be a risk factor for negative mental health outcomes. In other words, there's a normative rate of brain development, and we can either be too quick or too slow, and we should care about that. And I agree. And if you do a non-systematic review on Google Scholar looking for accelerated maturation and brain and MRI, you find about 27,000 papers that consider this question of accelerated brain maturation. But what does brain maturation mean? What does it really mean? Well, the standard approach is to use age-heterogeneous cross-sectional studies. In other words, we image children, usually ones, who vary in some dimension of interest. So they vary in age, they vary in SES, they vary in the degree of adversity they've experienced. And then we can relate this thickness to the outcome we might care about. So we extract the thickness as a proxy for maturation because we know what the curve looks like, and we can then compare children who differ in cortical thickness as a proxy of maturity. Which leads to lots of papers like this, which go on this emotional roller coaster, and I see this title of this paper, Cortical Thinning is Associated with Disease Stages in Dementia and Parkinson's, and I get very excited because I'm interested in longitudinal brain development, and then I get to the abstract, and then thinning has changed into thickness. In other words, it's not thinning, it's people who differ in cortical thickness. And the problem is that if we don't study development as it actually unfolds over time, we can't resolve different developmental processes. Because this is not a direct measure of brain maturity. Because maturity ultimately is a within-person, individual-level concept. It's something that happens to you, to your brain, and you are at a certain stage of maturation. And if we want to understand whether you're acceleratedly maturing or not, we need to study you. So why is this a problem? Well, it's a problem because observed differences are ambiguous. So imagine we scan a number of children who differ on some dimension, and they might also differ on age. And we find that they differ in cortical thickness. We could say, well, this child with a kind of less cortical thickness is probably further along this developmental curve. But we can easily show that this is ambiguous because the source of these differences between children, so why one child has a greater or a lesser cortical thickness, might be the difference in the total amount of thinning, or in the rate of thinning, or in the onset, so a child might start later or earlier, or they might simply start with a greater cortical thickness and mature at exactly the same rate at exactly the same time. But if we only scan them once, we don't know which of these scenarios, or which mix of these scenarios we are actually operating in. So it doesn't allow us to say one child is more mature than another. So we cannot resolve the source of observed differences with cross-sectional data alone. They might be kind of a proxy, but they don't tell us what we actually want to know. So what we wanted to set out to do in this project was to measure brain maturity, what we would consider properly. So the model we proposed is inspired by work by Dan McNeish, and it's a four-parameter logistic model, and it's relatively simple. It looks a bit like this, which is very similar to the raw data curves you saw before. We have 4 parameters. We have the upper asymptote, so how thick is your brain at the start of maturation. Your lower asymptote, where does it end? The thinning rate, and then crucially, the parameter we care about most is our quantitative definition of maturity, which is the midpoint of cortical maturation, which you can see here highlighted by the red dot. So that's the estimated age at the inflection point of cortical thinning. In other words, if I study your brain development, what's the age and what's the exact age at which your thinning starts to slow down? Because that's, in principle, it's independent of how thick your cortex was to start, how thick it is at the end, and even of the rate of thinning. So we can really isolate what we consider the definition of cortical maturity, which is when does your thinning start to slow down? And it gives us a way to grasp this thing we're actually interested in. Because it allows us to properly separate these distinct parameters for further investigation. So we can then say, well, independent of someone's cortical thickness when they were, say, 6 or 7 or 8, they are now more or less mature than someone else. Because crucially, for each of these parameters, we can estimate random effects. In other words, for each individual in our population, given suitable data, we can get an estimate for each of these parameters. In other words, I can say something about your asymptote, your upper asymptote, your lower asymptote, and crucially, the age of your inflection point. And then we can then use model selection techniques to decide, do I need to allow these different parameters to differ between people? The problem is that to do this, the demands on the data we need and on the estimation of these models are high and until recently out of reach. So why are they out of reach? Well, first and foremost, because we don't have or didn't have enough longitudinal data. So a few years ago, Dr. Ivan Simpson-Kent and I did a review of longitudinal cognitive neuroscience of intelligence. So this is not all longitudinal imaging studies, but a specific focus on those studies that have both longitudinal cognitive ability and longitudinal brain measures. So we tried to find any paper we could find. And we ended up finding 22 longitudinal developmental studies, which are very interesting studies. But this is essentially all of them until very recently. And just for some kind of sense of comparison, is 22 a lot or is it a little? It's half as much as papers on dog MRI. Now, I'd be the first to advocate that this is adorable and we should do more of it. But crucially, the longitudinal development of something as fundamental as general cognitive ability, we should have more data to try to understand it properly. Luckily, there are innovations on the horizon. We've heard about several today. And there's a collaboration we started on with this wonderful group in Denmark, because our goal was to estimate all parameters of this model, of this growth trajectory at the individual level. So we really need high temporal resolution developmental imaging data. So the Hubu sample, led by Catherine and William Barré, are now up to 15 waves. So they scan these children every 6 months. And when you ask them about it, they give you this long stare. It's like, yes, I wish we knew what we started on. But they're still doing it. So when we started on this, they were on 12 waves, but now they're up to 15 waves. So they've been imaging these children every 6 months. So for the first time, in kind of a very meaningful way, we can actually see a child's brain develop. So we're going to combine this kind of unique data set with this 4PL model with random effects. So we set out, and we were very kind of eager, and we had a plan, and we had a finish line. We were going to do this. So we looked at this kind of how do we model these types of effects? Which tools do we use? We went to our shed to grab the best tool, and there were actually many, so we were delighted. We should have been more worried at that stage when there was a paper that already in the abstract said, euphemistically, these types of models often encounter numerical errors. That should have been our warning to run away. Luckily, Delia did not. So reality was far more like this. So we tried a multitude of packages that people have used for thousands of kind of different applications. And essentially, none of them worked. So it wasn't possible to estimate these models with random effects, which is what we wanted to do. So only when we actually wrote the developer of one of these packages and said, please help, this should be possible, but it's not. And she helped us with a fix in this package, and then finally we were able to do it. So we could estimate these models at the individual level. So what do we conclude, or what do we find? So this gives you these curves, and I can sit here and look at these curves all day. These are 100 kids' brains actually developing. It's magic. So what are the fixed effects? What are the population level averages? Well, we found an upper asymptote of almost 3 millimeters and a lower asymptote of 2.5 millimeters. In other words, you lose about 0.5 millimeter of cortical thickness through various physiological mechanisms. So the average age of maturity of this, our definition of maturity, this inflection point, was 14.5 years. But crucially, we needed random effects. In other words, we needed to allow for individual differences in the upper asymptote, so people start somewhere different, which you can immediately see at the top here. We needed random effects for the lower asymptote, so people end up somewhere different. And crucially, we needed random effects for the age of maturational inflection. So what that taught us, which is maybe not surprising to some of you, but it's still kind of a way to quantify this idea, is that there are individual differences in the age of maturation, at the age at which your cortical thinning starts to slow down. So on the right here, you can see the estimates of the inflection point for all these 100 children. You can see these huge differences, up to 6 years at the age of this maturational inflection point. So you can see some of the children are already at age 13 or kind of 13 and a half. They're basically already slowing down their cortical thinning. And you can see this person, he or she, all the way on the right, whose inflection hasn't onset even at age 18. So you might think, as we did, that this is essentially measurement error, but we can look at the individual fits of the individual lines to each participant in our sample. And I believe this is the person here on the top right, so you can see this model is really fitting the data quite well. So this person on the far right really is quite fundamentally different in many ways than the other participants. We can really zoom in on one individual, their brain development over time. So inspection of these individual plots and the precision of our parameter estimates make us confident that these findings are reliable. So people really differ up to 6 years in this onset of inflection. We also find individual differences in total thinning from 0.5 millimeter to only 0.2 millimeters. And we find different beginnings and different endings. So we find substantial differences between individuals from kind of 3.5 millimeters to 2.5 millimeters, as well as their lower asymptote. And there's a moderate positive correlation, so those with thicker cortices tend to maintain those thicker cortices all the way through development, but it's far from perfect. We find some evidence for sex differences, in that we replicate that males have slightly but significantly thinner cortices at baseline and slightly later maturation, although we have relatively few males, so we're not particularly confident in this group comparison. But interesting for us, like, why go through all the trouble of estimating all these parameters? Well, we find that 3 of these 4 random effects are needed, even in this relatively modest sample size. And the parameters we estimate, so the hill is essentially the rate of thinning, and then you have the lower asymptote, the upper, and the inflection point, and they're only weakly correlated. So they tell us something unique and something different and distinct about each individual. So the implication is we must model all 4 of these estimate parameters to truly capture development. So we could then also take this kind of brain average thickness and look at regional effects. So we looked at the kind of Desikan-Kiliani atlas, so we can estimate these curves at the level of each specific ROI. And we could then compare a model where we fix the inflection point to be equal across regions. In other words, we can test the hypothesis. To first approximation, is the inflection point the same across all these brain regions? To a model where we allow it to differ. And the model with the freely estimated inflection point fit the data much better. So what that tells us is that brain regions differ in the onset of cortical thinning, but perhaps not in the way that at least some of you would expect. Because to our surprise, and contrary to several previous findings and claims, is some of the earliest regions were the frontal pole. Now, I looked in several textbooks, and that's definitely not what's supposed to happen. Frontal regions are thought to be late maturing, and of course, this is only cortical thickness. This doesn't tell the whole story about cortical maturation, but it's an interesting story. And interestingly, when we looked at the data, it also gives us a reason why we think people believe frontal regions to mature late rather than early. Because even though our estimate of the frontal pole tells us this maturational onset is relatively early, it's at 13.9 for the frontal pole, if we look at the raw data of the frontal pole, you see it's a relatively thick brain region. So it starts kind of, some people have a frontal pole that's 4 millimeters thick, and even the lower asymptote of the population level is closer to 3 millimeters, which is actually the upper asymptote for the brain on average. In other words, by measuring people only once, the frontal pole looks like a thick region, and a thick region is not finished maturing. So if we only take these cross-sectional snapshots, we mistake the frontal pole for a region that still has to mature. When we actually study maturation as it unfolds, the frontal pole is relatively early to mature. Because you can see the average population here, the upper asymptote is 3, whereas that's only where the frontal pole ends. So in our data, at least, we find that the frontal pole matures early, but it's more thick than other regions. So we find that maturation is regionally and individually specific. So to summarize these findings, the midpoint of cortical maturation is a distinct property of cortical thickness development, which we can separately estimate from other measures. And it's defined as the age of onset for this slowing of cortical thinning. And by allowing this combination of new models that we didn't have and new data that we didn't have, we can, for the first time, make this empirical conclusion that there are substantial differences in brain maturity between people and between regions. And there are these multiple components of maturity which likely have distinct physiological underpinnings and vulnerabilities and consequences. So what are some of the open questions of this project? As well, how does maturity relate to external factors, such as adversity or telomere length or cognitive performance and change? What is good maturation? What is less good maturation? And can we quantify maturational mismatch and disparity in health as well as in disease? And also methods questions. How many or how few waves do we need to reliably estimate these shapes? And at what ages should we best measure brain structure to get the richest picture of cortical maturation? How can we best zoom in on cortical maturity as it unfolds? So these are just some of the questions that this work opens up. So shifting gears a little bit from brain changes and brain dynamics to behavioral dynamics. I've spoken about this kind of idea of a high-resolution snapshot. So those are the classic individual differences. We try to paint the best and most accurate picture of why some people differ to others. And I've argued in the first empirical example that instead we should focus more and more on change, on longitudinal samples that allow us to study change as it unfolds over months and over years. And in the last section, I want to focus instead and zoom in even further on intra-individual variability. So if we really zoom in, not at the age range of years, but at the range of seconds, what do we find there? So I'd like you to imagine two children, Charles and Ada, who do some computerized test in a school setting, say. So they do a test, and then the results come out, and they both have a mean performance of 6. Now this happens all the time, every day. CITO scores are essentially like this. Sit down, do a test, your score is 6. And that might mean you get to go in the extra challenges class, or you might need a little bit of extra support. Usually that's where we stop, and by we, I also mean myself. But we can, of course, take a deeper look, deeper dive, and we can say, well, where does this 6 come from? And we look at the trial level data of this performance. And you can see immediately that Charles has these pronounced peaks and troughs, these ups and downs that go from quite high scores to quite poor scores, whereas Ada scores much more reliably within a far narrower band of performance. So what we want to understand and what we want to know is, where do these peaks and troughs come from? Do they tell us something interesting about cognitive development? So what is cognitive variability? Well, in the simplest scenario, imagine a simple reaction time task where your job is to press a button as quickly as you can whenever you see it appear. So cognitive variability is the difference in performance within the same person across trials or across sessions or across days. And it's generally a neglected source of individual differences. And neglected, I also mean by myself. I tend to study test scores, but not the source of those test scores. Where do they come from? What are the raw data that lead to a mean score of 6 or of 10 or whatever it might be? So you can think of cognitive variability at different levels of resolution. So it might be within a trial, it might be between trials, or between sessions, if I give you a test in the morning and the afternoon and the evening. Or it could be between days. Do you have good days and bad days? And are your good days and bad days more pronounced than someone else's? So why is cognitive variability important? Well, firstly, we have reason to believe that variability is distinct from the mean, from your mean performance or your median performance, and it has unique predictive information. Variability can lead to misstratification with lifelong consequences. So in the Netherlands, we have quite kind of high-stakes testing. So your score on a CITO essentially governs to a large degree which schools you're allowed to be stratified into. So imagine again Charles with his average score of 6. Well, he might be tested on a day where he does indeed score 6. But he might also be tested on a day where he either exceeds his average performance or scores far worse, which means he ends up in a school that is not particularly well suited to his educational needs and abilities. We also have reason to think that variability might be a sensitive early marker of atypical development that tells us something we didn't already know by just studying the mean. And finally, this is more of a mystery. Can we distinguish adaptive versus maladaptive variability? Are there types of variability that are good and other types of variability that are bad? So why do we know so little about variability compared to our knowledge of mean performance? Well, it's hard. So people have been proposing this intra-individual variability as something we should care about for at least half a century. And the reason is it's hard to measure well. So we can give them children pencil and paper tasks, which they might do if you kind of reward them suitably once. But if you ask them to do it again and again and again, they'll start to throw tasks at you and pencils. It's also hard to model well. So how can we really zoom in on variability as distinct from these other phenomena? Because we have reason to think that simple models conflate distinct sources of variance. In other words, if we use classical models, we're not really capturing variability the way we commonly think of it. And the proper models are hard to estimate, like the ones I showed before, and require Bayesian estimation. So how do you measure variability? Well, imagine some continuous task, such as reaction time or such as accuracy, as long as it has a continuous metric and a number of trials. So the standard metrics to quantify variability is to simply compute the ISD, the intra-individual standard deviation. So I take all your trials, and instead of a standard deviation across people, I take the standard deviation across trials. And then a person with a large standard deviation has a lot of variability, and the small standard deviation has little. Now that's a decent first approximation, but it doesn't really capture the stuff we're actually interested in, because it conflates differences in ability, in learning rates and inertia, and true variability. In other words, all these distinct signals that are in our trial level data, we throw them on a heap, and that's not really what we want to do. To give you an extreme example, you can see these 3 trajectories across trials here at the bottom. So you can see they're incredibly similar in terms of their peaks and troughs. So in many ways, kind of most of us would conclude that these 3 individuals are very similar in their variability. When actually, if you compute the ISD, the variability of the top line will be 10 times as large as the variability of the bottom line. The reason is the change in performance, so this person either gets a lot better or a lot worse across trials, is considered part of the ISD, so it's accidentally taken on board as contributing to variability. So what we want to do is capture our intuition that these 3 lines are somewhat similar in their variability quantitatively. So how do we do that? So we use tools called dynamic structural equation modeling, and we can model the trial level data as 4 parts. Firstly, we have the mean. So you have 2 individuals here in red and in blue, and the individual in red is very quick, and the individual blue is relatively slow. That's kind of bread and butter. You've all computed these types of performance metrics. But we can also simultaneously estimate the trend. You can think of the trend as training or growth, your improvement over time, or as fatigue or boredom, your slowing over time. And we can estimate probably the most kind of nebulous of concepts of autoregression or inertia. What inertia captures is the degree to which you have streaks where you either exceed or perform worse than your own average. And it's a bit hard to see, but you can see, for instance, the person in blue has higher inertia than the person in red, because the person in blue has these streaks of trials where they're either slower than their own average, and then they're faster than their own average. And once we've taken into account those 3 sources of individual differences, we can then compute residual variability. Once we've adjusted those other sources, we can then say, well, what's left? And that's the thing we're interested in. So imagine we have reaction time, or log reaction time at time t for a person I, and this will be some math. So the raw data looks a little bit like this for one person. So we can then study it as a source of all of these 4 components. So their reaction time at a certain trial is a function of their mean. So you can see in gray a person who's relatively quick, and in red a person who's relatively slow. Their trend, so that's the blue component, the improvement or worsening over time, the autoregression or mean reversion or inertia, and then the residual variability, which here is denoted in green. So you can see the person here in green has a mean that's somewhere between red and gray, but has a much higher residual variability. And then crucially, once we estimate these parameters, we can estimate random effects. In other words, do people differ on each of these parameters? Do they differ on the means? Probably, because we've done 100 years of that research. Do they differ on these other components? And what does that tell us about their development? So how do you interpret DSEM models? Well, it gives you a model DIC, which is an information criterion, and it basically tells you, do we need all this hassle? Do we need to estimate all these additional parameters? Is the complexity of my model justified by the better explanation of my data? Secondly, and most interesting for someone like myself who's interested in differences between people, do we need to allow these parameters to differ between people? And if we do, in other words, if some people have higher or lower scores on these parameters than others, how are these differences related to the outcomes of interest, such as age, performance, mental health symptomatology, and brain structure? So I'll walk you through two empirical examples. Firstly, relating variability to neurodevelopmental disorder symptomatology, and secondly, variability in the neural noise hypothesis. So this is work together with Nanda Rommelse and Michael Aristodemou, and the wonderful COTAP collected by Professor Nanda Rommelse, which has over 1,000 children between 5 and 13, who did 6 different blocks of choice reaction time tests that differed a little bit in manners that doesn't really matter for the results I'm showing you here, but allows us to study reaction time variability in this kind of group that has a relatively high prevalence of either subdiagnostic, for instance, neurodevelopmental disorder symptomatology. So what do we find? Across all the blocks, all 4 of the dynamic components were necessary. In other words, we needed all of these parameters to tell us something to explain the data we observe. And all 4 needed random effects. In other words, the people or the children in our sample, they differ in their mean ability or their mean speed. There were some trends, even across a small number of trials, so even across 20 or 30 trials, people improved a little bit or worsened a little bit. The children differed in inertia, and crucially, they differed in variability. Overwhelmingly so. So some children were more variable than other children. And we can estimate this variability in as few as 30 trials. So we really don't need that much data to be able to conclude that some children have this pattern and some children have this pattern. So what are the mechanisms of variability? Well, first we looked at the, kind of as a sanity check at the age effect, and we found that older children were much less variable. So you can see that they decrease in their variability quite a bit. So that could be for a variety of reasons, maybe less fatigue, less boredom, but also decreases in task strategy. But one thing you might start to question right now, so isn't this just telling us the same thing as your mean response time? Aren't they just kind of isn't this a really complicated way of measuring the thing we can already do quite well with a mean or a median? So a way to check whether the variability is telling us something distinct about age or distinct about performance is to regress some outcome we might care about, such as mean accuracy or age or symptomatology, on both variability and mean reaction time simultaneously. Because if the variability is telling us something we didn't know already, then that should give us unique predictive information above and beyond the mean. And we tend to find across the board, across all blocks, that variability tells us something unique that the mean didn't already tell us. In other words, it's something we can estimate reliably with relatively few trials, and it tells us something we didn't already know. So in the next step, we wanted to relate this variability to phenotypes we cared about, including neurodevelopmental symptomatology. So we looked at the SWAN scale for ADHD, which has 2 distinct dimensions of inattention and hyperactivity. And also, because we wanted a broader view, we also looked at the SDQ, or the Strength and Difficulties Questionnaire, which has these 5 different dimensions. And the reason we wanted to look at all 5 is we wanted to see, does variability just globally relate to symptomatology, or is there something specific about it? So what do we find? Well, we found remarkably specific effects for subcomponents of ADHD. We found that children with greater ADHD symptomatology, especially inattention, were more variable. In other words, variability predicts inattention, but not hyperactivity to nearly the same degree. And most interestingly, across 6 blocks, we looked at these 5 different dimensions of the SDQ, and we find that variability does not relate to any of them, yet it relates to in every single block, variability relates to inattention and hyperactivity. So this kind of variability is really specific. It's not just noise, it's not just kind of some measurement error, it's really specific to inattention subdimension of ADHD. So why do these findings matter? Well, there's some reason to think that this variability is central or mechanistic to ADHD. Because in a very large meta-analysis of including pharmacological intervention trials, Károly et al. Found that if you give children methylphenidate or Ritalin, which you don't give to affect their reaction time variability, because who cares? But if you give them methylphenidate, you find almost a standard deviation decrease in the reaction time variability in these children. And that did not happen for other interventions. In other words, when you give children medication to help their inattention or their kind of ADHD symptoms, you get this variability in reaction time along for free, which suggests to me that, at least in principle, it could be something that is fundamental or kind of mechanistic to ADHD. So a speculative possible follow-on project to see, are there other ways that aren't pharmacological to decrease variability? Could we train children to decrease their variability across trial rather than what we now do in schools is only focus on your mean performance? So try to do better, try to meet some threshold. Can we teach anyone to decrease their variability by giving them feedback? And if we do, does that transfer to other domains? So the second application of studying variability is variability in the neural noise hypothesis. And this is work with Ethan McCormick, who is somewhere here behind the blinding lights. Is we wanted to study variability in brain structure. So there's a large kind of hypothesis, a large literature on this idea of neural noise hypothesis. In other words, in your brain, there's this intrinsic neural noise that is affected by brain structure and function. And one plausible mechanism is myelination of axonal fibers. In other words, this fatty tissue that wraps around axons decreases the Gaussian noise. And by decreasing the Gaussian noise, it decreases the variability of the signal, or the signal transmission between two regions. Now, this is plausible, but the data we have so far are usually small samples and clinical cases. In other words, you compare people with extreme myelination degradation to, say, typical controls. So we want to see, can we find this relationship between myelination and variability in a relatively healthy sample? Because we hypothesize with individuals with better indices of white matter will have less variable performance, because the more insulated your axons are, the less variable the signal transfer will be, and ultimately that will manifest as less variable reaction time performance. So the data we use here is the CAMCAN sample that I worked on as a postdoc, the Cambridge Center for Aging and Neuroscience, which has almost 3,000 adults, of which we were able to image 700, and you can apply for the data for free. The age range is 18 to 102, so it's always slightly magical that I get to touch the data of 102-year-olds. I feel like I should be wearing gloves. And the data I'm analyzing is a simple reaction time task that just looks like this. 50 trials, respond as quickly as you can, go. So we're going to try to make some sense out of this. And we found support for the neural noise hypothesis, because we can estimate variability, and as before, we found that people differ in variability, but we then wanted to see, well, does that tell us something about myelination? So in this figure, you can see how two simultaneous predictors, white matter microstructure and age, predict these various components of our DSEM model. And we found that those with better white matter are faster and less variable above and beyond the effects of age. So it's not just the case that older people have this kind of degradation of their myelination and they also become more variable. Even though we already take into account the effects of age, white matter myelination tells us something, or a proxy of myelination, tells us something about reaction time variability. So the better insulated your axons, the less variable your reaction time performance is. We found some tract specificity with the strongest effects in the anterior thalamic radiations, which connects the prefrontal cortex to the thalamus and is associated with cognitive and motor control. So it's a somewhat plausible tract to find to have a relatively strong effect. And crucially, this effect was hardly attenuated by including age. So we're not just kind of interpreting age in a slightly convoluted way. So myelination is really telling us something specific. So how do we want to extend this work? Well, there are many ways I want to extend this work, but I'll talk about two. So firstly is behavioral. So this is a collaboration with the Karolinska Institute, with Nick Judd and Torkel Klimberg, who took these standard, boring cognitive tasks that children don't want to do unless you pay them, and turned them into a game that looked fun on an iPad. They called it the Vector app, and it looks a bit like this, and children can win points. And if children can win points, then 300,000 of them will do so. And I last checked 2 weeks ago, and they kindly shared this data with us, and we're currently up to 850 million items, which is quite a lot. I suspect the effects will be significant, whatever they are. We also want to extend this work in the neural dimension. So there's a wonderful data set that we hope to dive in over the next months and years. Not just looking at MRI and fMRI, but taking actual intracranial recording. So this is a wonderful data set that has these electrodes inserted into the brain, recording neural signals at the neural level, as well as reaction time and accuracy data. So we might be able to take the squiggles of behavioral performance and relate them to the squiggles of brain performance and really see, can we test this neural noise hypothesis, not with these indirect cross-sectional estimates of myelination, but with your actual brain noise as it happens over time. And a final brief plug for the starting grant, Codec, where we want to extend this work by studying 600 children longitudinally, because we know almost nothing about what variability tells us about how children are likely to develop. So we want to see, if I know you're a variable right now, what does that tell me about your future? Is being variable and flexible maybe a good thing, or is it a bad thing? Or are certain types of variability good and other types of variability bad? And what are the causes and consequences of variability? So over the next few years, I'll be hiring a postdoc, a PhD student, and an RA. So if you're interested and you either speak or want to learn Dutch, then let me know. So to summarize, if we combine new models and new data, that will lead to new findings. And I've talked about two today. We can define, capture, and estimate a precise definition of cortical maturity using suitable data and quantitative approaches. And we can zoom in on these microscopic differences and changes in cognitive performance. That tells us something we can't simply answer by looking at your mean performance, revealing new insights into cognitive development. So if I've convinced you to use some of these tools, in terms of models, there are many resources online, but one I can recommend particularly for longitudinal data is this wonderful resource over here that has all these kind of hands-on tutorials on how to teach yourself these models. And in terms of data, there are many out there, but we recently wrote a paper that gives you some overview of some resources that are there. And we made an OSF spreadsheet, so if you have a data set that is not yet in there, then we're very eager to expand it and add it and update it. So to conclude, development matters, and if we use new models and new longitudinal data, we can answer new questions and make new discoveries. And I would argue this is the most exciting time yet for being a developmental cognitive neuroscientist. And on that note, I'd like to thank funders, lab members, and mascots. Thank you very much.
Thank you for this wonderful, inspirational talk. Are there any questions from the audience? Yes, there. Oh, yeah, go ahead. Yeah, no, go ahead.
I'll just ask a really short one. So thank you, Rogier, for this super talk. It was a blast of science, fantastic, really fun. I was wondering if you could speculate a bit about well, the functional meaning of the variability. You ended your talk with a lot of questions, but I think you might have some answers already that you're thinking about. So in the L-CID data, we're always looking for differential susceptibility markers. And I was wondering if you think of the variability also as a possible differential susceptibility marker in such a way that, of course, you can train it to make people more stable, and maybe that has benefits in some parts of your life, but possibly the same sensitivity in other parts of your life may be a benefit, for example, that you adapt quicker to changes in the environment. So do you think that variability can possibly be a differential susceptibility marker in such a way that it can help you for better and for worse?
Yeah, so to answer your first question, what variability is, I think probably lots of things. So the simplest thing is the thing we saw in ADHD, so it's just inattention. It's, do you essentially fail to respond or fail to focus? And people can fail to focus even when they're staring at the screen. So even if you have eye trackers, people still zone out, and we all do so every now and then. But there's also reason to believe that in childhood, at least, that there are variabilities that are good, so that reflect task strategy exploration. So there's this kind of strategy mixing. You see children, the more complex the cognitive task, the more strategies they will try out, and they will tend to try out 1, 2, 3, 4 strategies, and then at some point they zoom in on the one they consider best, and then they kind of basically settle on that. So we think that for more complex tasks, but one of the questions we don't really know for sure, is that variability on a complex task when you start out is probably a good thing, because you don't want a 4-year-old who is set in his or her ways, and you want them to explore the world and to try out various things. So we have reason to believe that variability is a marker of strategy use and exploration as well as inattention. So one of the goals for Codec is to see, can we separate those two? Can we identify good and bad variability? The other thing we know is that children who make these developmental kind of almost Piagetian jumps in their development, so you see that in L2 developments of children learn an extra language, you can see these discontinuities in language performance. And right before children make this jump, they tend to be far more variable in their performance. So it could be that variability is essentially a necessary step on the way to the next level of achievement. So that's another thing we want to capture, but that's a different kind of variability because it goes away again after you reach this new plateau.
So you argue that it can be variability that's good and that's bad, but maybe it's the same variability that in some circumstances helps you and in other circumstances hurts you.
No, I agree. So the example I had kind of before until, well, you imagine a surgeon you probably don't want to have a lot of variability. In fact, do you want a surgeon who has a mean score of 8 with a large standard deviation or a mean score of 7 with no standard deviation? Well, I'll pick the second one. And there are other types of jobs where you want that type of dependability. But in our artists, we probably want mad flashes of genius. We want them to exceed their own performance because that's the peaks that matter. So there probably isn't a single way that is best overall. And to kind of circle back to your question on differential susceptibility, I think one of the reasons that this is interesting is that I suspect children who are more variable get missed out for additional support because as long as they meet some minimum threshold, they don't get additional support for dyslexia, for reading, because if you can read well enough at a certain time. But if you have 2 children with the same score, then Charles in the example spends 10 or 20% of his time below some threshold where actually he might need additional support. So children who are more variable are going to spend some time, some proportion of their time in a regime where they could use support. So I suspect those children could be at risk because they look like they're fine because they can meet some threshold if they need to, but actually they spend 10, 20, 30% of their time in a regime where they need more help. I think it's probably the same for mental health. So if you have a large standard deviation of your mood, for instance, then that's probably a marker for more vulnerability than people who have a very stable, if lower than average mood, for instance.
Andrik, could you please stand up? Yes. So that people online can also see who asked the question.
Thanks, Rogier, for your very inspirational talk. Also, I couldn't agree more that this is the time to do this type of analysis. And I was interested about your first part, actually, on the inflection point and upper asymptote, because I have to give a bit of background. I did this latent class growth analysis where you basically also are able to see whether people differ on the intercept or the slope. And across a couple of studies now, exploratory study by the way, we actually see in structural brain data quite some intercept differences. And I tend to interpret this together with colleagues as a window of opportunity for structural brain development defined by the intercept. Because if you look at the slopes, the lines of individual growth, they tend to be quite parallel. So now my question, how did you already explore the variability in the upper asymptote between people and the inflection point? Because it's a lovely technique to model the data. But I was wondering whether you have any hypothesis or data already to see whether they both predict certain outcomes.
So we did look at so we found we definitely needed a random effect for the upper and the lower asymptote. That they were also somewhat correlated, but far from perfect. So there's definitely differences in the intercepts of where the children start, as well as where they end up. And we found, crucially, that you can look at the inflection point correlation here at the bottom row. You can see the correlation between this maturational inflection and the other parameters, so your thickness and your thinness, so to speak, is relatively modest. In other words, there's definitely something distinct about the inflection point as it relates to the upper asymptote. So I think that's something kind of relatively separable. I don't know if that answers your question, but.
Yes, I was also surprised by surprised, I'm not sure. If you link it to an outcome, so basically it's an invitation maybe to let me know when you have that data, because it's really crucial and nice to see what's the best predictor. So
that's entirely legitimate. So we debated, so there's kind of debated whether to not incorporate those in here. So we ended up not doing it for a few reasons. A, because we think this is intrinsically neuroscientifically interesting. So regardless of what it predicts or not, this tells us something about brain development that we didn't know, at least didn't know for sure until now. Secondly, these are the types of children who come back 15 times. They are not your average child, and they're probably not your average child in the average family because they don't come back 15 times for various reasons. So this will be a future project in this sample to relate this to cognitive performance, maybe to their environmental markers, but my suspicion is A, 90 isn't large enough to draw strong conclusions either way, and B, this will be a relatively narrow slice of not just the global population, but even the Danish population. But my suspicion is that this would allow us ultimately to predict this inflection point as a function of early adversity, for instance. I find it entirely plausible that experiencing kind of high degrees of adversity or extreme adversity early on might make you mature more quickly. In other words, that means your inflection point should shift to the left. So I think that's plausible, but we haven't done it in here just yet, also because we have collaborators who spent a decade collecting this data, so we can't wander in and grab everything. And I think because this won't be the definitive word either way. This is 90 children of probably relatively kind of well-off environment. So even if we don't find strong associations, I think there's still future work to be done in the types of studies like L-CID and ABCD to really answer these questions.
Thanks.
There's a question from Olga. If you could please stand, yes, thanks.
Hi, thank you so much for the interesting presentation. I'm very inspired. I was wondering, because you were talking about how the variability gets less over time, or has like a turning point in which it becomes less. And in ADHD, that was kind of maybe not that much observed because the variability was much larger in the ADHD sample. And I was wondering, because for ADHD there are a lot of papers that report that there is a delayed cortical maturation. That is, of course, before you explained, that is mostly cross-sectional and maybe not reliable. But do you think that that could be an indication as well for delayed cortical maturation in ADHD, or do you think there was a higher starting point and that it got less over time?
Yeah, it's a great question. So again, as I said, I don't necessarily think these hypotheses are implausible or untrue. It's just that we probably need more data than we thought we did or we'd like to need to be able to answer it conclusively. I think it's entirely plausible that you'll find that type of pattern in ADHD or symptomatology. I should say, I use the word ADHD, but this is not necessarily a sample of children who have received a formal diagnosis. They just vary continuously in the symptoms. But I think it would be plausible to think that perhaps this reflects delayed maturation, delayed cortical maturation, but I don't have data to attest to that yet. So.
Thanks, that would be interesting to see.
Okay. Thank you so much. I have one more question.
Yeah.
Because the HUBU data is quite exceptional in all those time points, and there are no other data sets out there like that, right? So yeah, what would be an ideal data set? Like, do you have some advice for like everyone working on longitudinal data sets? How should it look like? How many data points? How many long in between the data points?
Well, if someone could scan 100,000 children every 6 months, that'd be fantastic.
Okay. Yeah,
no, but so I did ask them, if you did it again, what would you do differently? And they kind of said, essentially, they would probably, and it depends on which metric you care about, probably subsample less frequently, so more around every 9 months, would probably give you all the benefits with less scanning occasions. Mm-hmm. So one of the things we want to do now with both this data and simulated data is, if we know the ground truth of these trajectories and we input these random effects, can we see how little data we need and at what ages we need to measure these children to basically get the best bang for our buck? Because if we image, say, children every 6 months when they're 6, they're probably most of them will be right at the peak of their kind of increase in cortical thickness before their decrease starts. So we're probably not going to get much in the way of slope estimates. So our data suggests that around 14, 15, the change is quickest on average at the population level, which means if you sample more densely there, maybe every 6 months, you're going to get a lot of kind of the information there. So what I would argue is that we should use these simulation-based tools to see, well, how can we, if we only have 1,000 scanning occasions to spend, rather than always stick with the kind of classical design we're used to, like we must scan at exactly the same interval once a year, because that's what we've always done, and that's what the grant office will pay us for, is how can we maximally use the number of scanning occasions we have? And my suspicion is it'll be focusing more on critical periods and having a lot of planned missing data, so skipping a lot of measurement occasions, we probably can get a lot more precise estimates of the parameters we care about for the same amount of money. So consult your friendly neighborhood statistician and they'll tell you what to do.
Yeah, well, really nice that you think about the practical implications as well and how you can actually do this. Yeah. Thanks a lot for your talk. I think we have a new topic for another conference to talk about development and variability matters. So maybe in a year. Thanks a lot.
Thank you very much. Thank you very much. Thank you. Let me just grab this. Too many things.
Oh, hier zit er nog aan vast. Ja. Okay, we will now move to the last part of today's section. We not only have been working on, sorry, can I get some presenter notes, please? We have not only been working on this conference for the last couple of months, but we've also been working on a website in which we present our open science goals and aims and products that we have as an output from the Leiden CID study. And it's my pleasure to, for the first time, show you this brand new website today. But first, a little bit about why we made this website. So now, after 8 years of data collection, we don't only want to share the outcomes and the papers that we wrote, but also be as open as possible and give you a little bit of a peek behind the scenes in how we conducted this, this study. And there are many reasons on why you want to share this and why you want to be open in science and conduct open science. But we brainstormed a lot about why it's important to us. And this is really important, these values, because it will show in all our open science products that we are designing. So first, we believe that being open will improve the quality of our work if we can show what we have done exactly. We can get input from the scientific community and improve our work. And another advantage is that if we can share what we've done, we can also help improve other researchers, set up their research, and don't invent the wheel all over again and share our practices learned. And by sharing our data where we can, we also promote reproducibility and replication, which is highly needed in the field of developmental neuroscience at this time. And furthermore, by sharing our work, we can save scarce resources and time from other research to invent the wheel all over again. But also very important to us is that we're very grateful that all the participants and their parents came into the lab every year again, or we visit their home, so it's a very intensive research that they took part of. So by sharing data where we can, other questions can be answered without collecting data of 1,000 children all over again and their families. So this highly reduces participant burden. So in our open science practices, we highly value transparency, findability, and accessibility. And with each open science initiative, we first put them to the test whether they actually meet these values. So our generation of scientists, we are the scientists of the future. And we're very thankful for getting the opportunity to think about how this looks like. So in our open science solutions, we envision the future generation of scientists. And therefore, we do not only want to share what we have learned, but we like to build a platform where scientists can come together and share their experience with the scientific community, to everyone working on developmental model data. Yet how great this vision may sound, there are many challenges to actually translate this into practice. For once, we have so much data and so many protocols. As such, we need to find solutions to still make this accessible and findable. So all these ideas together, combined, resulted in building this website, where all our open science solutions will become available and accessible in a way. So are you ready to see for the first time what we have built? Our homepage, and we thank Lisbeth Smit for working with us on this website and a beautiful design. So you land on our homepage, you see exactly what we've been doing, what our study, what our questions are that we ask, what our values are, why we want to be open, our team with our very ambitious plans. You can find blogs in where we share our lessons learned and our best practices for conducting science. You can explore our research. We are developing a metadata explorer. You can see exactly what kind of study design we have, how many waves, what kind of children, what kind of measures we have. And we also try to make it a little bit fun. So you see that here, you can click around, so play around on our website. Different measures, so you see the home visits, see the lab visits, and in this way we can give a really good overview of what is measured at what time. And finally, in the end, we also want to share our data, and we're still looking for working on solutions for that. But what we already share is our protocols. You can find them there. And we also already share protocols for sharing the data. So it's a long pipeline that we developed, and all the steps that you have to take to use the data in the end. So really thanks to our data managers, Mark and Simone, for setting this up. And this is also what we want to be open about. So thinking about all of these forums is already quite a process. You can read more about our open science vision on social impact and our goals. And we have many, many lessons that we want to share with you. So we thought a blog would be the perfect way to do so, to share on data collection, but also on data processing. So there are already a couple of blogs on there about today's morning workshop on open science, for example. There's going to be a blog on there soon from the societal impact workshop. So if you missed that, read on it. And we would also like to invite you to post questions so we can help you out. But most importantly, this is a big, big team effort. There are many, many people involved. The founders that founded the study, of course. We have the current team that is working on this. We have many, many collaborators. So you can find each individual expert. You can contact us if you think this is interesting to you and you'd like to know more about their work. Our collaborators, which work at Leiden and at the VU. Many PhD students already successfully defended their PhD, and 3 more will come soon. And all of the alumni and over 140 students that already worked on this project. Can you believe it's so many? So please find us online on developmentmatters.nl, email us, find us on Twitter and LinkedIn. And for now, I would like to thank the whole team. Please come on stage, because we did this really as a collaborative effort. So I would like to invite you to come up here.
on, isn't this wonderful? Let's give one more round of great applause. It was a great day. I'm so proud of the group here, of all the alumni, so happy with all my collaborators in the room, everybody who came to visit. It was really a wonderful day. Let's go celebrate a little bit more and have drinks together. Hope to see you at the drinks.